Hello there, and welcome to Cosmos for Sleep. Tonight, we're drifting through the fascinating realm of light, exploring its incredible speed. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy, and let's begin. The speed of light in a vacuum is the universal constant, denoted as c, representing the fastest possible speed for anything in the cosmos. This fundamental constant defines a cosmic speed limit, a boundary that nothing with mass can ever reach or exceed. It is a cornerstone of our understanding of the universe, governing how information, energy, and even gravity propagate through the vast emptiness of space. This unwavering speed underpins the very fabric of reality, influencing everything from the smallest subatomic particles to the grandest galactic. Hello there, and welcome to Cosmos for Sleep. Tonight, we're drifting through the fascinating realm of light, exploring its incredible speed. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy, and let's begin. The speed of light in a vacuum is the universal constant, denoted as c, representing the fastest possible speed for anything in the cosmos. This fundamental constant defines a cosmic speed limit, a boundary that nothing with mass can ever reach or exceed. It is a cornerstone of our understanding of the universe, governing how information, energy, and even gravity propagate through the vast emptiness of space. This unwavering speed underpins the very fabric of reality, influencing everything from the smallest subatomic particles to the grandest galactic structures. It is a constant that shapes the flow of time and the perception of distance, revealing a universe far more intricate and interconnected than our everyday experiences might suggest. This profound constant, universally denoted by the elegant single letter c, it stands as a majestic and immutable truth within the fundamental laws of physics, representing the swiftest possible velocity that anything can achieve across the vast and tranquil stretches of the cosmos. This c is not just an arbitrary measurement, a mere numerical value on a chart. It is an intrinsic, deeply embedded property of our universe, a fundamental constant that defines the very pace at which all forms of information and energy can ripple through the silent, boundless expanse of space. It sets the rhythm for cosmic interactions, from the most minuscule quantum exchanges to the grandest, most leisurely dance of galaxies. This singular speed dictates the inherent tempo of the universe, ensuring a harmonious and predictable unfolding of events across billions of years. Its very existence establishes a cosmic rhythm, influencing every interaction from the smallest quantum events to the largest celestial phenomena. It is a concept that invites contemplation, revealing a universe where speed itself has a definitive, unyielding boundary. Imagine a tranquil, boundless ocean, and c is the ultimate, most graceful wave that can traverse its surface, unimpeded and unyielding, carrying whispers of distant stars across its shimmering surface. This universal constant forms the very bedrock of modern physics, guiding our understanding of how the cosmos operates and how its many components interact. It is the intrinsic velocity of causality, ensuring that effects always follow their causes in a predictable and orderly sequence, maintaining the serene coherence of the universe. This constant is not merely a theoretical construct, but a deeply observed and experimentally verified aspect of nature, a silent sentinel of cosmic order, ensuring that the universe adheres to its own elegant design. Its constancy provides a stable framework, allowing for the precise calculations that unveil the hidden patterns of the cosmos and the subtle ballet of its constituents. Indeed, this inherent speed of light serves as the ultimate cosmic speed limit. It is a profound and unyielding barrier that ensures nothing with mass, no object composed of particles, can ever reach or surpass this extraordinary velocity. The implications of this limit are far-reaching and deeply woven into the fabric of reality, creating a fundamental distinction between massless particles, like photons, and all other forms of matter. scientists have meticulously explored the consequences of this barrier, discovering that attempting to accelerate an object with mass closer and closer to the speed of light would require an ever-increasing, indeed an infinite, amount of energy. This means that while light itself glides effortlessly through the void at its maximum velocity, any physical entity, from a tiny dust particle to a colossal starship, is forever bound to a slower, more patient journey through space. This gentle constraint is not a dramatic barrier that imposes a harsh restriction, but rather a fundamental characteristic of existence, ensuring a harmonious and predictable cosmic order. It establishes a natural boundary for all physical interactions, preventing instantaneous travel and preserving the delicate balance of cause and effect throughout the universe. This intrinsic limit underscores the elegant design of the cosmos, where even the most energetic processes must adhere to this ultimate speed, allowing for the gradual and stately unfolding of cosmic events. Without this limit, the universe as we know it, with its vast distances and the orderly progression of time, would simply cease to exist, dissolving into an incomprehensible chaos. The very stability of matter and the progression of cosmic history are gently cradled within this unyielding speed constraint. To be precise, light travels at an exact and unchangeable rate of 299,792,458 meters per second when traversing the emptiness of a vacuum. This specific numerical value is not merely an approximation, a close guess at a grand phenomenon. It is a precisely defined constant, now serving as the basis for many other fundamental measurements in physics. This level of exactitude underscores the foundational role of light's speed in our scientific understanding of the universe. It is a number that has been meticulously measured and verified through countless experiments, standing as a testament to the precision of cosmic laws. This constant offers a stable anchor in the ever-unfolding mysteries of space and time, providing a reliable reference point for all cosmological calculations. Its exactness allows scientists to define the meter, the fundamental unit of length, in terms of the distance light travels in a specific fraction of a second, thereby linking space and time through this profound cosmic speed. This universal definition removes any ambiguity, ensuring that measurements across the globe, and indeed across the cosmos when observed, remain consistent and perfectly aligned with the inherent properties of light itself. The sheer magnitude of this number, hundreds of millions of meters in a single second, evokes a sense of both the immense speed and the vastness of the distances light routinely traverses. A silent, swift journey across cosmic realms. For those who may find meters per second a less intuitive measure, this incredible speed is approximately equivalent to 186,282 miles per second. To put this into a more relatable perspective, imagine light circling our entire planet Earth. At this phenomenal speed, a beam of light could complete roughly 7.5 circuits of the equator in a single second. This rapid journey across Earth's circumference highlights the dizzying velocity involved, a speed that dwarfs any speed we experience in our daily lives, making even the fastest human-made vehicles seem utterly motionless by comparison. Consider that a commercial jet travels at hundreds of miles per hour, yet light covers hundreds of thousands of miles in the blink of an eye. This equivalence helps to paint a clearer picture of the sheer, breathtaking rapidity with which light dances across the cosmic stage, an unhurried yet incredibly swift journey that shapes our perception of distant celestial events. It is a speed so immense that it becomes almost abstract, yet it is utterly real and constantly at play in every photon that reaches our eyes from the tranquil depths of space. This swiftness allows light to traverse the immense gulfs between stars and galaxies, carrying information from the furthest reaches of the observable universe to our waiting telescopes, a quiet cascade of ancient illumination. It is also important to consider that the term light encompasses a much broader spectrum than just what our eyes can perceive. All forms of electromagnetic radiation, a vast and vibrant family of cosmic messengers travel at this very same speed in a vacuum. This includes the subtle whispers of radio waves, which carry our broadcasts across vast distances and reveal the hidden structures of galaxies, the gentle warmth of microwaves, used in communication and to study the universe's oldest light, the unseen glow of infrared light, which pierces through cosmic dust to reveal new star formation, the energetic dance of ultraviolet light, vital for life, but also indicative of intense stellar activity, the penetrating gaze of X-rays, used in medical imaging and to observe the fiery environments around black holes, and the powerful pulses of gamma rays emitted from some of the cosmos's most energetic events, like the gentle merging of neutron stars. Each of these different forms, while varying in wavelength and energy, shares this common, fundamental velocity when moving through empty space. They are all expressions of the same underlying electromagnetic force, united by their unwavering speed, carrying diverse information across the cosmos in a synchronized, silent flow. This unity of speed across the electromagnetic spectrum is a testament to the elegant simplicity and profound consistency of the physical laws that govern our universe, allowing us to perceive and study the cosmos in its full, radiant complexity, a harmonious symphony of invisible and visible energies. One of the most profound and perhaps counterintuitive aspects of the speed of light is its remarkable constancy for all observers. This means that regardless of your own motion, whether you are standing still on Earth or soaring through space at an immense velocity aboard a spacecraft, a beam of light will always appear to be traveling away from you at precisely the same speed, c. Similarly, the motion of the light source itself, whether a distant star or a nearby flashlight, has no bearing on the speed at which its light reaches you. Unlike ordinary objects, where relative speeds can vary, for instance, if you run toward a ball, it approaches you faster, and if you run away, it approaches slower. Light maintains its absolute velocity. Imagine a car driving down a road. Its speed relative to you changes depending on whether you are standing still or driving in the opposite direction. Light, however, follows its own unique and unchanging rule, a testament to its singular nature. This principle challenges our everyday intuition, where speeds typically add or subtract, but it is a deeply verified truth that forms the bedrock of modern physics. It ensures a universal framework for understanding motion and interaction, regardless of the observer's particular state of movement, maintaining a serene consistency throughout the universe's grand design. This unchanging speed provides a universal reference, a cosmic constant that allows for the consistent measurement of space and time, regardless of one's perspective within the vast, tranquil expanse. This extraordinary invariance, the fact that the speed of light remains constant for everyone, everywhere, under all circumstances, is not merely an interesting observation. It is a cornerstone of Albert Einstein's revolutionary special theory of relativity. Published in 1905, this theory fundamentally reshaped our understanding of space and time, demonstrating that they are not separate fixed entities, but rather interwoven components of a single dynamic fabric known as space-time. Einstein's insights, built upon this constant speed of light, revealed that concepts like simultaneity, duration, and length are not absolute, but are instead relative to an observer's motion. For instance, time can appear to slow down, and distances can seem to contract for objects moving at very high speeds relative to an observer, a subtle yet profound warping of reality. This elegant and profound theory transformed physics, offering a new lens through which to view the universe's most fundamental workings, guiding our exploration of cosmic mysteries with serene precision. It is this unwavering speed of light that binds together the dimensions of space and time, creating a unified and beautifully consistent framework for the entire cosmos, a silent testament to the genius of Einstein and the profound elegance of nature itself. The constant nature of light's speed thus underpins the very structure of our physical reality, revealing a universe that is both predictable in its fundamental laws and endlessly fascinating in its implications, continually inviting us to ponder its subtle depths. Now, let us turn our gaze closer to home, to the delicate ballet of light within our own solar system. As we greet the morning sun or watch its gentle descent below the horizon, we are engaging with a phenomenon that is not entirely in the present moment. Light from the sun, the radiant core of our planetary family, embarks on a journey that takes approximately 8 minutes and 20 seconds to reach Earth. This means that every ray of sunlight warming our skin or illuminating our world carries with it a memory of the past. We are, in essence, always seeing the sun as it was 8 minutes and 20 seconds ago. If a colossal solar flare were to erupt on its luminous surface, its brilliant light would not reach us instantaneously. There would be a measured, unhurried delay of just over 8 minutes before its glow became visible in our skies. This subtle temporal displacement highlights the vast, yet often imperceptible distances even within our cosmic neighborhood, reminding us that even our closest star is observed through a gentle veil of time. It is a serene thought, knowing that the light that bathes our planet has already completed a considerable journey, a silent messenger from a moment just a little while ago. Our closest celestial companion, the Moon, offers an even more immediate, yet still slightly delayed, visual experience. When you direct your gaze toward the Moon, observing its placid cratered surface, you are seeing light that has only recently departed its reflective terrain. This lunar light completes its brief voyage across the relatively short distance to Earth in about 1.3 seconds. This fleeting delay means that the Moon you perceive in the night sky is merely 1 1/3 seconds in your past, a nearly instantaneous echo of its present state. The difference between the Sun's 8-minute journey and the Moon's brief 2.1 trip underscores the varying scales within our solar system, from the immense gulf to our star to the comparatively intimate proximity of our natural satellite. This tiny temporal window allows for an almost real-time connection with the Moon, yet it still gently whispers of light's finite, though swift passage across space, a continuous, subtle reminder of cosmic distances. Venturing further outward, the journey of sunlight to the red planet, Mars, becomes noticeably longer. On average, sunlight travels to Mars in about 12.7 minutes. This duration, however, is not a fixed constant. The time it takes for sunlight to reach Mars varies subtly with the planet's orbital positions. As both Earth and Mars follow their distinct paths around the Sun, the distance between them is constantly changing. When the two planets are at their closest approach, the light travel time is shorter, and when they are at their farthest points, the journey lengthens. This graceful orbital dance means that our view of Mars, whether through telescopes or in photographs sent by robotic explorers, is always a glimpse into a moment that transpired roughly 12 to 20 minutes ago. This measured delay impacts our communication with the uncrewed missions exploring the Martian surface, requiring patient planning for every command and every data transmission, a testament to the unhurried nature of light's cosmic travel. Continuing our serene tour of the solar system, we arrive at the majestic gas giant, Jupiter. For light from the Sun to reach this colossal world, it takes approximately 43 minutes. This substantial delay showcases the growing distances as we move away from the inner rocky planets and into the realm of the outer giants. When we observe Jupiter's swirling clouds or its prominent Great Red Spot, we are witnessing a scene that unfolded nearly 3/4 of an hour in the past. This significant time lag means that any real-time control of spacecraft orbiting Jupiter is impossible. Commands must be sent well in advance and responses received long after the event has occurred. The 43 minutes of light travel time for Jupiter is a gentle yet powerful illustration of the vastness of our solar system, where even light, the swiftest known entity, requires a considerable amount of time to bridge the immense gulfs between worlds, providing a tranquil sense of cosmic scale. Our journey to the very edge of the recognized planetary family brings us to Neptune, the most distant planet from the Sun. For sunlight to arrive at its icy, remote surface, it takes over 4 hours. This extended travel time, spanning more than 240 minutes, means that Neptune is perpetually observed in a state far removed from its present. When we glimpse its faint blue disk through powerful telescopes, we are seeing light that began its immense voyage across billions of kilometers, many hours before it ever reached our planet. This 4-hour delay underscores the profound distances that define the outer reaches of our solar system, where the sun's light, though still powerful, has stretched itself across a truly immense cosmic canvas. The long duration of light's journey to Neptune serves as a quiet reminder of the patient unfolding of cosmic processes and the sheer scale of the space that separates us from even our closest planetary neighbors. Beyond the planets, the finite speed of light becomes an even more pronounced factor when communicating with distant spacecraft, such as the intrepid Voyager probes. These pioneering robotic explorers, having ventured far beyond the traditional boundaries of our solar system, serve as our silent ambassadors to the interstellar void. The signals they send, and the commands we transmit to them, are forms of electromagnetic radiation, traveling at the speed of light. However, because of the immense distances involved, these communications experience significant and unavoidable delays. A simple question sent from Earth to Voyager, or a data packet transmitted back, is not a real-time exchange, but a slow, unhurried dialogue across astronomical scales. This patient form of communication highlights the practical implications of the cosmic speed limit, transforming what we perceive as instantaneous communication on Earth into a measured, deliberate conversation with our most distant outposts. To illustrate this profound delay, consider the journey of a radio signal sent to Voyager 1, which is currently the farthest human-made object from Earth. A command transmitted from Earth to guide its instruments or adjust its trajectory can take over 23 hours to reach the spacecraft. Once Voyager 1 processes this command, any reply or data it transmits back to Earth embarks on an equally long return journey, also taking over 23 hours. This means that a complete round-trip conversation, a single exchange of information, spans more than 46 hours, or nearly 2 full Earth days. Such an immense delay necessitates extraordinary patience and meticulous planning from the scientists and engineers who continue to monitor and guide these distant probes. It is a powerful, tangible demonstration of the vastness of interstellar space and the unyielding nature of the speed of light, transforming what would be a quick chat into a leisurely, multi-day cosmic dialogue, a silent testament to the enduring reach of human ingenuity across the tranquil depths of the universe. This intrinsic characteristic of light, its finite yet immense speed, bestows upon us a truly remarkable ability. Observing distant objects is inherently like looking back in time. It is a profound, tranquil truth that transforms every celestial gaze into a journey through cosmic history. As light begins its long, patient voyage from a distant star or galaxy, it carries with it an indelible imprint of that moment in time. By the time those photons finally reach our eager eyes or sensitive telescopes, eons may have passed. We are not witnessing the immediate, present state of these celestial bodies, but rather a gentle echo of their past selves. This phenomenon is not merely a scientific curiosity. It is a fundamental aspect of how we perceive the cosmos, turning our universe into a vast, living archive where every point of light tells a story from long ago. It is a silent, unhurried form of time travel, where the cosmos itself serves as our guide, slowly unveiling its ancient tapestry, one delicate photon at a time. The light we gather is a messenger, a silent traveler that has traversed unimaginable distances, carrying with it the very essence of a bygone era, allowing us to connect with moments that unfolded long before human civilization began its own journey. This quiet passage of light ensures that the universe always offers us a glimpse into its own serene and ongoing evolution. When you gaze at the shimmering tapestry of stars in the night sky, allowing your thoughts to drift among their silent brilliance. You are not perceiving them as they exist in this very instant. Instead, you are seeing them as they were hundreds, thousands, or even millions of years ago. The faint twinkle of a nearby star might represent light that left its surface during a time when humanity was just beginning to explore its own planet. A more distant nebula's soft glow could be illumination that departed during the age of dinosaurs, or even further back, before complex life even emerged. This temporal displacement is a constant, subtle reminder of the vastness of space and the measured pace of light's journey. It means that the cosmos is a dynamic, ever-changing entity, and the picture we receive is always slightly out of sync with its current reality. A star we observe tonight, for instance, might have undergone a significant transformation or even ceased to exist thousands of years ago. Yet its light continues its solitary voyage across the interstellar void, reaching us as a serene whisper from its past. This gentle delay allows us to ponder the enduring nature of starlight and the profound stretches of cosmic time it effortlessly bridges, offering a tranquil perspective on the fleeting nature of the present moment. Bringing this concept to a more tangible scale, consider the majestic Andromeda Galaxy, our nearest large galactic neighbor. The light that emanates from its countless stars and vast nebulae, which we observe as a faint, ethereal smudge in the night sky, began its immense journey approximately 2.5 million years ago. Imagine, for a moment, the Earth during that ancient epoch. Early hominids were just beginning to walk upright across the African plains, and vast changes were slowly unfolding across our nascent planet. The light from Andromeda has been patiently traveling across the intergalactic void ever since. A silent, unhurried messenger carrying images from a time long before modern humans existed. This 2.5 million year delay means that our view of Andromeda is a window into its distant past, a snapshot of its elegant spiral arms and glowing star-forming regions from an era of profound cosmic youth. It is a humbling thought, connecting our present moment directly to an ancient cosmic event that transpired eons ago, a testament to the enduring power of light to transcend vast stretches of both space and time, offering a glimpse into the serene and timeless dance of galaxies. Pushing the boundaries of our vision to the very limits of the observable universe, the light from the most distant galaxies visible to us departed billions of years ago. These are not merely ancient images, they are direct, ethereal glimpses into the very early universe, allowing us to witness the cosmos in its primordial stages. Through the patient gathering of these faint, stretched-out photons, astronomers can peer back across nearly 13.8 billion years of cosmic history. Each distant, shimmering point of light carries with it the story of a galaxy in its infancy, a time when stars were just beginning to coalesce and the grand structures of the cosmos were still taking shape. These faint, faraway beacons are silent witnesses to the universe's formative moments, offering invaluable clues about its initial conditions and the processes that guided its earliest evolution. It is a privilege to receive these ancient messages, these subtle whispers from the cosmic dawn, allowing us to reconstruct the majestic narrative of our universe's unfolding. A journey that began in serene simplicity and has gradually evolved into the intricate complexity we observe today. This extraordinary cosmic time delay is not just a poetic concept, it is a powerful tool that allows astronomers to study the universe as it appeared in its infancy, offering a unique and unparalleled window into its evolution. By observing galaxies at varying distances, scientists can effectively create a timeline of cosmic development. The light from closer galaxies shows us relatively recent epochs, while the light from the most distant ones reveals a much younger universe. This layered perspective enables researchers to trace the formation and growth of the first stars, the assembly of the earliest galaxies, and the gradual chemical enrichment of the cosmos over billions of years. It's like having a series of photographs taken at different stages of a long, slow process, each one revealing a distinct chapter in the universe's grand story. This ability to look back in time is fundamental to modern cosmology, providing the empirical evidence needed to test and refine our theories about the Big Bang, cosmic inflation, and the ongoing expansion of space. It is a tranquil form of cosmic archaeology, patiently unearthing the universe's past to understand its present and anticipate its future. Among these ancient cosmic messages, the most profound and oldest light we can detect is the cosmic microwave background radiation. This pervasive, faint glow fills every corner of the universe, a silent, omnidirectional hum of ancient energy. It is not light from any particular star or galaxy, but rather the cooled afterglow of the Big Bang itself, originating nearly 13.8 billion years ago. Imagine the universe in its earliest moments, a hot, dense, opaque fog of plasma. As it expanded and cooled, a pivotal moment arrived when it became transparent, releasing this flood of light. This cosmic microwave background radiation is therefore a direct relic from the universe's fiery birth, a gentle whisper from the very dawn of time, continuously bathing us in its subtle, ancient radiance. Its discovery was a monumental achievement in cosmology, providing compelling evidence for the Big Bang theory, and fundamentally altering our understanding of cosmic origins, acting as a serene, ever-present memory of the universe's earliest state. This ancient light, the cosmic microwave background, offers an invaluable snapshot of the universe when it was only 380,000 years old. To grasp the significance of this, consider that our universe is currently estimated to be approximately 13.8 billion years old. 380,000 years is a mere fraction, a fleeting moment in this immense cosmic timeline. At this remarkably early stage, the universe had cooled sufficiently for protons and electrons to combine, forming neutral hydrogen atoms. This event, known as recombination, allowed photons, the particles of light, to travel freely through space for the first time without constantly scattering off charged particles. Before this, the universe was an opaque, dense soup. After, it became transparent, allowing light to journey across vast distances. Thus, the cosmic microwave background is a pristine image of the universe in its profound infancy, a primordial blueprint encoded with subtle variations that would eventually grow into the galaxies and clusters we observe today. It is a silent, profound testament to the universe's humble beginnings, a delicate glimpse into its earliest moments, offering a tranquil window into the very first chapter of its majestic story, revealing the subtle seeds from which all cosmic complexity would later gracefully unfold. As we journey further into the cosmic tapestry, it becomes essential to grasp the unique units used to measure the universe's immense scale. Many often mistake a light year for a measurement of duration, but it is in fact a fundamental unit of distance, not time. It elegantly quantifies the immense path that light, our swiftest cosmic messenger, traverses in the span of one Earth year. This distinction is crucial for comprehending the true scale of the universe, allowing us to accurately chart the vast spatial separations between celestial bodies, rather than their temporal relationship. The light year defines a cosmic mile marker, a tranquil measure against which the immense separations of stars and galaxies are gently laid out, providing a serene framework for understanding the expansive canvas of space. It is a poetic, yet precise metric, allowing us to conceptualize distances that defy ordinary terrestrial scales, transforming abstract numbers into comprehensible cosmic journeys. This unit helps us to bridge the gap between our human experience of distance and the truly colossal scales of the universe, offering a calm and steady way to map the boundless void. To fully appreciate the vastness encapsulated within a single light year, let us consider its staggering numerical value. 1 light year is approximately 9.46 trillion kilometers. For those who prefer a different scale, this translates to about 5.88 trillion miles. These numbers, while immense, begin to paint a picture of the extraordinary distances involved in cosmic travel. To put this into perspective, imagine traveling around the Earth's equator. you would need to circumnavigate the globe roughly 236 million times to cover a single light year. Even the fastest human-made spacecraft would take tens of thousands of years to travel just 1 light year, underscoring the profound scale of this unit. This immense distance, covered by light in a mere year, highlights the unhurried journey that photons undertake across the interstellar medium, carrying their silent messages across vast, tranquil gulfs. It is a distance that stretches the imagination, yet it is merely the first step in measuring the truly colossal dimensions of the cosmos, a number that quietly whispers of the universe's boundless nature. This numerical description provides a tangible sense of the expansive environment in which stars and galaxies peacefully reside. Bringing this unit into focus with a specific celestial example, the nearest star system to our own, Alpha Centauri, is located about 4.37 light-years away. This means that the light we perceive from Alpha Centauri, that gentle twinkle in the southern sky, began its journey through space over 4 1/3 years ago. If, by some cosmic happenstance, Alpha Centauri were to suddenly diminish its radiance or even cease to exist, we would not become aware of this change for more than 4 years. This enduring delay underscores the profound temporal separation that even our closest stellar neighbors maintain. The light from Alpha Centauri serves as a tangible reminder of the light year's practical application, allowing us to not only measure its distance, but also to understand the inherent time lag in our observations. It is a silent, patient journey for those photons, spanning trillions of miles to reach our eyes, carrying a serene echo of a moment that has already gently passed. The proximity of Alpha Centauri, while vast by human standards, is a mere step in the grand cosmic distance ladder, a testament to the quiet immensity of our local stellar neighborhood. Expanding our perspective from a single star system to a grander scale, our home galaxy, the Milky Way, is an exquisitely vast cosmic island. Its majestic spiral arms stretch across approximately 100,000 light-years from one edge to the other. To truly comprehend this scale, imagine a celestial city of unparalleled proportions, where billions of stars, vast nebulae, and dark matter are gracefully arranged in a flattened disk. Our own solar system, with its sun and planets, resides within one of these spiral arms, embarking on a long, leisurely orbit around the galactic center. The sheer breadth of the Milky Way, measured in these immense light-years, paints a picture of a truly colossal structure, a universe within itself, teeming with countless wonders and silent mysteries. It is a sprawling, tranquil expanse where light takes an extraordinary amount of time to traverse from one side to the other, highlighting the profound distances that define our galactic home. This measurement provides a serene sense of our place within this grand, rotating system, a tiny speck within a vast and beautiful stellar ocean. The concept of the Milky Way's vastness becomes even more profound when we consider the ultimate speed limit of the universe. Even if one could theoretically travel at the speed of light, an unimaginable feat for any object with mass, it would still require an astonishing 100,000 years to traverse our galaxy from one edge to the other. This thought experiment underscores the truly immense scale of our galactic home. It means that a journey across the Milky Way, even at the maximum possible speed, would span a duration far exceeding the entirety of recorded human history. This inherent temporal constraint, imposed by the speed of light and the galaxy's sheer size, ensures that the Milky Way remains a realm of slow, unhurried processes and vast, patient journeys. It reminds us that even light, in its relentless swiftness, is subject to the profound distances that define the cosmos, offering a tranquil perspective on the grand scale of galactic existence. The idea of such a long journey, even at light speed, allows us to appreciate the serene, enduring nature of cosmic structures, which unfold over truly astronomical timescales. Venturing beyond the confines of our own galaxy, we encounter the truly staggering scale of the observable universe. This immense sphere of cosmic reality stretches approximately 93 billion light-years in diameter. It represents the spherical region of space whose light has had sufficient time to reach us since the universe's fiery inception, the Big Bang. This observable aspect is crucial. It does not necessarily define the entire universe, which may be infinitely larger, but rather the portion from which information has had the opportunity to travel to us across billions of years. Within this vast luminous sphere reside countless galaxies, each a cosmic island like our own, separated by immense gulfs of expanding space. The edges of this observable universe are not physical boundaries, but rather a temporal horizon, a gentle limit imposed by the finite age of the cosmos and the unwavering speed of light. It is a profound thought that every direction we look, we are gazing into a sphere of past light, a tranquil memory of the universe's grand unfolding, a vast, luminous testament to cosmic history. This boundary, though constantly expanding, acts as a serene reminder of the limits of our perception within the boundless cosmos. Ultimately, the elegant concept of a light year serves as an indispensable tool, helping us to comprehend the immense, almost unimaginable scales of the cosmos and the profound distances that separate celestial bodies. Without this unit, expressing the vastness of space would be relegated to numbers so large they lose all meaning, becoming abstract figures devoid of intuitive grasp. The light year, however, provides a relatable framework, linking the finite speed of light to the boundless expanse of the universe. It allows us to speak of distances in terms of light's journey, transforming the abstract into something more tangible and poetic. This unit provides a tranquil bridge between our human perception and the grand cosmic reality, fostering a sense of wonder and humility as we contemplate the universe's majestic dimensions. It is a silent guide, helping us to navigate the intricate architecture of stars, galaxies, and voids, revealing the serene and interconnected nature of all things, inviting us to reflect on our delicate place within this vast and beautiful cosmic design, a constant whisper of the universe's enduring grandeur. As we continue our gentle journey through the cosmos, we encounter another profound connection to the speed of light, the pervasive influence of gravity. According to Albert Einstein's groundbreaking general theory of relativity, gravity itself does not act instantaneously across the vastness of space, but rather travels at the exact speed of light. This means that gravity is not a static, omnipresent force, but a dynamic phenomenon, propagating as gentle changes or ripples in the very fabric of space-time. Imagine dropping a pebble into a tranquil pond. The ripples spread outwards at a finite speed. Similarly, any alteration in a massive object's gravitational field, such as a star gently shifting or a planet slowly moving, sends out a subtle disturbance that travels at sea. This elegant concept profoundly alters our classical understanding. Where gravity was once thought to be an immediate pull, revealing instead a universe where all fundamental interactions, including gravity, adhere to the same universal speed limit. It is a harmonious dance, where light and gravity are intrinsically linked, each moving with the same unhurried grace through the cosmic expanse, ensuring a coherent and predictable unfolding of celestial events across vast stretches of time and distance. This intrinsic connection means that gravity's influence is not a sudden, abrupt command, but a patient, measured communication across the cosmos, a fundamental aspect of how the universe maintains its serene order and interconnectedness. This understanding of gravity as a propagating influence, rather than an instantaneous one, adds another layer of subtle complexity to the majestic cosmic ballet. This profound principle has a fascinating and tangible consequence, illustrating the delicate interplay between light and gravity in our own solar system. If, by some unimaginable cosmic event, our radiant sun were to suddenly vanish from its central position, Earth would not immediately veer off into the cold, silent depths of space. Instead, our planet would continue its familiar orbital path, gracefully circling the now absent Sun for precisely 8 minutes and 20 seconds. This duration is not a coincidence. It is the exact amount of time it takes for sunlight to reach Earth. Only after this measured interval, when the gravitational disturbance caused by the Sun's disappearance has traversed the vast distance at the speed of light, would Earth finally begin to feel the change in gravitational pull. At that moment, it would gently drift away from its accustomed orbit, continuing its journey through the cosmos. This thought experiment beautifully illustrates that gravity's influence, like light itself, is a messenger with a finite travel time. It underscores the serene and predictable nature of cosmic interactions, where even the most fundamental forces operate with a measured patience. The delay in experiencing this gravitational change mirrors the delay in seeing the Sun's light disappear, a silent testament to the constant pace at which these cosmic influences propagate across the tranquil void, ensuring that the universe unfolds with a graceful and orderly progression, where every cause has its measured, unhurried effect. It is a quiet confirmation of the deep, intrinsic links between light and the invisible forces that shape our celestial home. Further expanding on gravity's elegant influence, massive objects, such as colossal galaxies and enigmatic black holes, possess an extraordinary ability to gently bend and subtly distort the path of light passing nearby. This phenomenon arises because these immense celestial bodies warp the very fabric of space-time around them, creating what can be imagined as gentle curves or depressions in the cosmic canvas. Light, in its unwavering journey, does not travel in a perfectly straight line through this curved space-time. Instead, it follows these subtle contours, its path gracefully diverted by the gravitational presence of the massive object. This is not a dramatic or violent twisting of light, but rather a placid, almost imperceptible redirection, a testament to the profound connection between mass, gravity, and the trajectory of photons. The more massive the object, the more pronounced this gentle curvature of space-time, and consequently, the more noticeable the bending of light. This ethereal interaction reveals that light is not merely a stream of particles traversing a static stage, but an active participant in the dynamic, flexible geometry of the cosmos, its path subtly guided by the unseen gravitational hand of immense structures. It is a beautiful illustration of how the presence of matter shapes the very pathways of light, creating an intricate and interconnected cosmic ballet, where even the void itself is subtly influenced, guiding the luminous messengers on their long, silent voyages. This elegant bending of light by massive objects gives rise to a truly remarkable astronomical phenomenon known as gravitational lensing. Acting much like an immense, natural cosmic telescope, gravitational lensing allows us to observe distorted or even magnified images of distant galaxies and peer into regions of the universe that would otherwise remain hidden from our view. When light from a far-off galaxy passes near a foreground galaxy cluster or a massive black hole, its path is gently curved, focusing and stretching the image of the background object. This can lead to captivating visual effects, such as the appearance of luminous arcs, complete Einstein rings, or even multiple identical images of the same distant galaxy scattered across the sky. These ethereal distortions are not optical illusions, but direct manifestations of gravity's subtle power to reshape the pathways of light. Astronomers skillfully utilize this lensing effect to study galaxies that are too faint or too far away to be observed directly, effectively using the foreground mass as a magnifying glass. Gravitational lensing also offers a unique method to map the distribution of dark matter, the invisible substance that makes up much of the universe's mass, by observing its gravitational influence on light, even though it emits no light itself. It is a tranquil and powerful tool, unveiling the universe's hidden structures and offering deeper insights into its grand architecture. A serene testament to the ingenious ways the cosmos reveals its secrets through the subtle manipulation of light. Among the cosmos's most enigmatic entities are black holes, and their profound interaction with light stands as a stark testament to the ultimate power of gravity. Once light crosses the boundary known as the event horizon, it cannot escape a black hole. This is because, at the event horizon, the gravitational pull becomes so extraordinarily strong that the escape velocity, the speed required to break free from its grasp, exceeds the speed of light itself. Since nothing in the universe, not even light, can travel faster than c in a vacuum, any photon that ventures beyond this point is gently, yet irrevocably, drawn inward, unable to ever return to the outer cosmos. It is not a violent capture, but rather a serene one-way passage into an unknown realm. The event horizon is not a physical surface, but a delicate, invisible boundary in space-time. A point of no return where the curvature of space becomes so extreme that all paths, including those of light, lead inexorably inward. This defining characteristic of black holes makes them appear utterly dark, as no light can emanate from within their event horizons to reach our telescopes. The concept reveals the profound limits that gravity can impose, even upon the swiftest entity in the universe, offering a tranquil contemplation of the ultimate boundaries of cosmic existence and the gentle, yet absolute power of these silent celestial giants to contain even light itself within their profound gravitational embrace. Beyond the steady pull of gravity, Einstein's general theory of relativity also predicted the existence of subtle ripples in the very fabric of space-time, known as gravitational waves. These ethereal waves are caused by some of the most dramatic yet elegant cosmic events involving accelerating massive objects, such as the graceful merging of two black holes or the serene dance of colossal neutron stars. When these incredibly dense objects gently spiral towards each other and finally coalesce, they create disturbances that propagate outwards through space-time, much like ripples spreading across a vast, placid lake. And just like light, these gravitational waves travel at precisely the speed of light, c. This fundamental connection means that gravitational waves are another form of cosmic messenger, carrying information about the most profound gravitational interactions across the universe at the ultimate cosmic speed. While they are incredibly subtle and challenging to detect, their discovery in 2015 by the LIGO experiment marked a monumental achievement, opening a new window into the cosmos. These gentle cosmic tremors allow us to listen to the universe in a completely new way, complementing our observations with light and offering fresh insights into the most powerful and distant celestial phenomena. It is a testament to the deep unity of cosmic laws, where both light and the very structure of space-time move in harmony at the same intrinsic speed, revealing the subtle yet profound interconnectedness of all cosmic phenomena, a quiet symphony of gravitational undulations. The very first observational evidence that supported this profound understanding of gravity's interaction with light came during a total solar eclipse in 1919. This pivotal moment in scientific history provided early, compelling confirmation for Albert Einstein's general theory of relativity. During the eclipse, the sun's brilliant light was temporarily obscured, allowing astronomers to observe stars whose light passed very close to the sun's limb. Einstein's theory predicted that the sun's immense gravity would gently bend the path of this starlight, causing the stars to appear slightly shifted from their true positions in the sky. An expedition led by Sir Arthur Eddington carefully measured these subtle shifts. Their observations precisely matched Einstein's predictions, providing undeniable empirical proof that massive objects indeed curve space-time, and that light follows these gentle curves. This serene confirmation was a triumph of scientific inquiry, transforming a revolutionary theoretical concept into an accepted truth and fundamentally altering our perception of the universe. It was a quiet yet profound validation of a new cosmic order, demonstrating that light, in its unwavering journey, is a sensitive indicator of the gravitational fields it traverses. This historical event marked a gentle turning point, ushering in a new era of understanding the elegant dance between light and gravity, and forever linking the two fundamental forces within the serene tapestry of the cosmos. It was a moment where the universe itself, through the subtle bending of starlight, whispered its profound secrets to awaiting humanity, confirming the intricate and beautiful elegance of its design. As we continue our exploration of light's remarkable journey, we now turn our attention to its graceful interaction with the very matter that composes our world. While light travels at its ultimate speed, c, in the vast emptiness of a vacuum, its pace changes perceptibly when it encounters a medium. Light slows down when it passes through substances like the clear depths of water, the shimmering surface of glass, or even the seemingly empty expanse of air, compared to its unhindered speed in a vacuum. This subtle reduction in velocity is a fundamental characteristic of light's engagement with material environments, transforming its swift, unimpeded glide into a more measured and deliberate progression. It is not a dramatic halt, but rather a placid adjustment, a gentle negotiation with the atomic structures it encounters. This slowing effect is imperceptible to our everyday senses. Yet it profoundly shapes how light behaves in our immediate surroundings, influencing countless natural phenomena and technological applications. The transition from the cosmic void to a material presence creates a delicate shift in light's journey, a testament to the intricate dance between energy and matter that defines our physical world, a silent, unhurried adjustment to its surroundings. The underlying mechanism for this gentle slowing of light is a fascinating dance between photons, the elementary particles of light, and the atoms within the medium. This reduction in speed occurs because photons are not simply passing through the material unimpeded. Instead, they are temporarily absorbed and then almost immediately re-emitted by the electrons within the atoms of the medium. Imagine a photon approaching an atom. It is briefly embraced, its energy temporarily transferred to an electron, which then becomes excited. Almost instantly, the electron returns to its original state, releasing a new photon that continues the journey. This continuous process of absorption and re-emission, repeated billions of times as light traverses the material, creates a slight but cumulative delay in the overall progress of the light wave. Each individual photon, in the brief moments between these atomic interactions, still travels at the speed of light in a vacuum. However, the collective effect of these momentary pauses, these tiny, gentle hesitations, results in a slower average speed for the light beam as a whole. It is a delicate, intricate ballet between light and matter, a silent conversation where photons are momentarily held before being serenely released to continue their luminous path, revealing the profound interconnectedness of energy and the atomic world. This unhurried interaction shapes light's passage through all transparent materials, from the air we breathe to the deepest oceans, ensuring a measured journey. To precisely quantify this subtle deceleration, scientists use a specific measure called the refractive index of a material. This value describes precisely how much light slows down when passing through a particular substance relative to its speed in a vacuum. A higher refractive index indicates a greater reduction in light's speed and a more pronounced bending of light as it enters or leaves the material. For instance, a vacuum has a refractive index of exactly 1, meaning light travels at its maximum speed. Air has a refractive index very close to 1, indicating only a minimal slowing. However, denser materials like water or glass possess higher refractive indices, reflecting a more significant interaction with light and a more noticeable decrease in its velocity. This elegant numerical value provides a clear and consistent way to characterize the optical properties of different substances, allowing scientists and engineers to predict and control how light will behave in various environments. It is a quiet yet powerful tool, unveiling the optical secrets of matter and enabling the creation of lenses, fiber optics, and countless other light-based technologies, all carefully designed around light's measured response to material presence. A serene testament to the predictable nature of its interactions. This fundamental change in light's speed as it transitions between different media is directly responsible for many familiar and beautiful phenomena we observe in our world. Consider the ethereal beauty of rainbows, those luminous arcs of color that gently stretch across the sky after a rain shower. Rainbows occur as sunlight disperses through countless tiny water droplets suspended in the air. As the light enters each droplet, it slows down and bends or refracts. Different colors of light, which are simply different wavelengths, slow down by slightly different amounts, causing them to separate. They then reflect off the back of the droplet and refract again as they exit, further spreading the colors into their magnificent spectrum. Similarly, the bending of light through a prism, creating a vibrant display of colors, is another elegant manifestation of this principle. When white light enters a prism, it slows down and separates into its constituent colors because each wavelength is refracted at a slightly different angle. These natural spectacles are not just visually stunning. They are serene, everyday demonstrations of light's patient interaction with matter, revealing the hidden spectrum within white light and the subtle physics that govern its journey through transparent substances, a tranquil reminder of the universe's inherent artistry. To provide a more concrete illustration of this phenomenon, consider the journey of light through the familiar medium of water. In water, light travels at about 75% of its speed in a vacuum. This means that if light could cover a distance of 4 meters in a vacuum in a certain amount of time, it would only cover approximately 3 meters in water during that same interval. This reduction is why objects submerged in water often appear distorted or displaced from their actual positions. A subtle optical illusion caused by the bending of light as it passes from the air into the denser water. The serene depths of oceans and lakes, therefore, gently slow the passage of sunlight, altering its trajectory and influencing the visual clarity of the underwater world. This measured decrease in speed is a constant factor for all light traveling through aquatic environments, affecting marine life and the way we perceive the submerged landscape. It is a tranquil, yet powerful, example of how a medium can influence the fundamental speed of light, transforming its otherwise unhindered cosmic journey into a more patient and interactive experience, a silent testament to the adaptable nature of light's path. Pushing this concept further, the interaction of light with extremely dense materials can lead to an even more significant reduction in its speed. For instance, in a diamond, light slows down dramatically, traveling at less than half its speed in a vacuum. This profound deceleration is responsible for diamond's renowned brilliance and fire, the dazzling sparkle that captivates our eyes. As light enters a diamond, it encounters a highly organized and dense atomic lattice, leading to more frequent and prolonged interactions with the electrons. This extensive engagement causes a substantial, reducing its effective speed by more than 50%. The light then refracts intensely as it exits the diamond, separating into its spectral colors and creating the characteristic scintillation. This remarkable slowing demonstrates how the inherent properties of a material can profoundly influence the velocity of light, transforming its swift cosmic journey into a more intricate and leisurely dance within the crystalline structure. It is a serene example of matter's capacity to gently yet powerfully modulate light's speed, revealing the hidden beauty that arises from these fundamental interactions, a tranquil display of nature's elegant optical artistry. Despite the observed slowing of light when it traverses a material medium, it is crucial to remember a subtle yet fundamental truth. Individual photons still travel at the speed of light in a vacuum in the brief moments between their interactions with atoms. The overall reduction in the average speed of a light beam is not due to any single photon itself slowing down, but rather to the cumulative effect of these momentary pauses. Imagine a serene river where the water flows smoothly and swiftly. Now imagine a section of that river filled with many small, gently turning eddies. A boat trying to cross this section might appear to move slower overall, not because its engine has weakened, but because it is constantly navigating around or briefly caught by these eddies. Similarly, a photon, in its intrinsic nature, always moves at c. It is the continuous process of being absorbed and re-emitted by the atoms within the medium that introduces the collective delay, causing the light wave as a whole to propagate at a reduced effective speed. This distinction maintains the integrity of light's fundamental constant, c, as the ultimate speed limit, while gracefully explaining its observed behavior in the presence of matter. It is a tranquil reminder that light's inherent velocity remains inviolable, even as its journey through the physical world is subtly, yet beautifully, mediated by the atoms it encounters, a silent, elegant dance of fundamental particles. This understanding of light's behavior in various environments brings us to a fascinating and sometimes counterintuitive phenomenon. While the speed of light in a vacuum, denoted as c, stands as the ultimate and unbreakable cosmic speed limit for anything with mass, a subtle distinction emerges when light enters a material medium. Here, a unique possibility arises. Particles can, under specific conditions, travel faster than the speed of light in that particular medium. This is a crucial nuance, as it does not imply a violation of Einstein's principles. No particle with mass can ever exceed the universal speed limit of light in the emptiness of space. Instead, it highlights that light itself experiences a measured deceleration when navigating through a substance, creating a gentle window where certain energetic particles, though still moving slower than c, can gracefully outpace the light waves within that specific material. This distinction underscores the adaptable nature of light's interaction with the physical world, revealing that its velocity is not always constant, but rather responsive to the environment it traverses. A tranquil testament to the intricate interplay of fundamental physics and material properties. The very fabric of space is constant, but the journey through matter introduces a different, more patient pace for light, allowing for this intriguing and beautiful cosmic exception. When a charged particle, such as an electron, accelerates through a transparent medium at a velocity exceeding the local speed of light within that very medium, it emits a distinctive blue glow. This ethereal radiance is known as Cherenkov radiation. It is a luminous signal, a serene visual manifestation of a particle gently breaking the light barrier in its immediate surroundings. Imagine a subatomic particle, moving with such swiftness through water or glass that it outpaces the light it would ordinarily generate in that material. This subtle, unhurried motion creates a ripple of electromagnetic energy, much like a boat moving faster than the waves it creates. The resulting light, a soft and pervasive blue, emanates in a characteristic cone shape, a visible signature of this extraordinary interaction. The transparency of the medium is essential for this phenomenon to occur, allowing the emitted light to propagate outwards and become visible. This gentle luminescence provides a direct, captivating insight into the behavior of high-energy particles as they navigate through dense environments, a silent dance of energy and matter that produces a truly unique and beautiful cosmic light. It is a placid display of physics in action, transforming the invisible world of particles into a visible, luminous spectacle. This remarkable effect, the generation of Cherenkov radiation, can be elegantly understood by drawing an analogy to a sonic boom, but applied to the realm of light. In acoustics, a sonic boom occurs when an object, such as a jet aircraft, travels faster than the speed of sound waves in the air. As the aircraft outruns its own sound waves, these waves pile up, creating a sudden, powerful compression that we perceive as a loud boom. In a similar, yet more subtle fashion, Cherenkov radiation arises when a charged particle breaks the light barrier in that specific material. The particle is moving so swiftly that it outpaces the electromagnetic waves it generates within the medium. Instead of these waves propagating ahead of the particle, they are effectively left behind in a coherent shockwave of light. This luminous shockwave is the Cherenkov radiation, a gentle, continuous emission of light that trails the particle's path. It is not a violent explosion, but a serene, measured release of energy, a quiet and beautiful consequence of a particle exceeding the local speed of light, illuminating its journey through the transparent substance. This analogy helps to visualize the elegant physics at play, transforming an abstract concept into a more intuitive understanding of how energy propagates through different media, a tranquil reminder of the interconnectedness of wave phenomena in the universe. One of the most well-known and captivating instances where Cherenkov radiation is famously observed is within nuclear reactors. Here, a characteristic blue luminescence emanates from the water that cools the reactor core, creating an ethereal glow that is both beautiful and scientifically significant. This serene blue light is produced by high-energy electrons, which are a byproduct of the radioactive decay occurring within the reactor's fuel rods. These electrons are ejected at speeds so great that they exceed the speed of light in water. As these swift electrons traverse the water, they generate the distinctive Cherenkov radiation, bathing the reactor core in a mesmerizing, otherworldly blue light. The water serves not only as a coolant, but also as a transparent medium that allows this unique phenomenon to unfold visibly. This placid, deep blue glow has become an iconic image associated with nuclear energy, a silent testament to the powerful subatomic processes at play. It is a tranquil, controlled display of fundamental physics, where the very forces of the atomic world interact with light in a way that is both profoundly energetic and visually serene, offering a gentle glimpse into the often hidden dynamics of matter and energy. Beyond the controlled environments of human technology, Cherenkov radiation also plays a crucial role in some of the most profound scientific endeavors, particularly in the detection of elusive particles like neutrinos. Neutrino observatories, often colossal detectors buried deep underground or submerged beneath vast expanses of ice, utilize this blue glow to detect these ghostly particles. Neutrinos are incredibly tiny, nearly massless particles that rarely interact with ordinary matter, making them extraordinarily difficult to observe directly. However, when a neutrino does, on rare occasions, interact with an atom within the detector's vast volume of water or ice, it can produce a charged particle, such as an electron or a muon, that moves at a speed greater than light in that specific medium. This secondary charged particle then emits Cherenkov radiation, creating a flash of blue light. The sensitive detectors, strategically placed around the volume, capture these faint light signals, allowing scientists to infer the presence and properties of the otherwise invisible neutrinos. This ingenious application transforms the subtle blue glow into a beacon of discovery, offering unique insights into the most distant and energetic cosmic events, from the heart of our sun to the furthest reaches of exploding stars. It is a patient and profound method, patiently waiting for the universe's most elusive messengers to reveal themselves through their luminous footprint, a tranquil and persistent quest for cosmic knowledge. The specific and consistent blue color of Cherenkov radiation is not arbitrary. It is a direct consequence of the physics governing its emission. This characteristic hue is due to the higher energy of shorter wavelengths being preferentially emitted during the process. When a charged particle generates Cherenkov radiation, it does so more efficiently at shorter wavelengths, which correspond to the blue and violet ends of the visible light spectrum. These shorter wavelength photons carry higher energy compared to their red or green counterparts. The mechanism of Cherenkov radiation favors the production of these higher energy photons, resulting in the distinct and vibrant blue light that we observe. It is a beautiful illustration of the subtle interplay between particle energy and the electromagnetic spectrum, where the energetic conditions of the emission intrinsically shape the visible color of the light produced. This spectral preference ensures that the Cherenkov glow is consistently a serene, deep blue, providing a clear visual signature for this particular physical phenomenon, a tranquil and predictable aspect of its luminous expression. Ultimately, the captivating phenomenon of Cherenkov radiation provides direct and compelling evidence that light speed in a dense medium is indeed slower than its speed in the vacuum of space. The very existence of this blue glow hinges on the fact that a charged particle can surpass the velocity of light within that material. If light were to travel at its maximum speed c in all environments, then no particle with mass could ever outpace it, and Cherenkov radiation would simply not occur. The observable fact of this unique luminescence, therefore, serves as a powerful, tangible validation of the principle that light experiences a measurable deceleration when interacting with matter. It is a serene confirmation of our understanding of light's adaptable nature, demonstrating that while c remains the universal cosmic speed limit, light's journey through the physical world is a more patient and nuanced one. This delicate interaction between light and matter is not a dramatic conflict, but a harmonious adjustment, revealing the profound consistency of physical laws and the subtle ways in which the cosmos expresses its fundamental truths through observable phenomena, a tranquil and enduring testament to the intricate beauty of scientific discovery. As we delve deeper into the nature of light, we must journey into the realm of quantum physics, where the rules of the cosmos reveal themselves in their most fundamental and often ethereal forms. Here, we encounter photons, the very fundamental particles of light, which embody a truly unique and profound characteristic. They possess no rest mass. This means that unlike the atoms and molecules that constitute our everyday world, or even the subatomic particles like electrons and protons, photons are not entities that can ever truly sit still in space. They are, in their very essence, pure packets of energy, perpetually in motion. Imagine a gentle, ceaseless flow of cosmic energy, continuously traversing the universe without ever settling into a state of repose. A photon is not a tiny solid sphere that can be weighed or brought to a halt. Rather, it is a fleeting manifestation of electromagnetic force, a quantum ripple in the fabric of reality that exists solely in its state of graceful, unceasing transit. This absence of rest mass is a defining feature that sets light apart from all other forms of matter, revealing a fundamental division in the universe's constituents. It implies that light is not bound by the same inertial constraints that govern objects with mass, allowing it an unparalleled freedom of movement. This intrinsic nature means that a photon's existence is synonymous with its journey, a silent, luminous dance across the cosmic stage, carrying its vital energy from source to destination. This elegant characteristic allows light to travel unimpeded through the vast, tranquil emptiness of space, a tireless messenger of cosmic events, perpetually carrying information without the burden of inertia. It is a subtle truth that speaks to the profound elegance and economy of fundamental physics, where light, in its purest form, is simply motion and energy intertwined. Because photons possess no rest mass, they are inherently compelled to always travel. This is not a choice or a variable. It is an absolute and unyielding condition of their existence. Photons cannot exist at any other speed. If a photon were to slow down, even infinitesimally, it would cease to be a photon as we understand it. This fundamental dictate of physics means that light is forever bound to its maximum velocity, a constant, swift progression through the cosmic void. Unlike particles with mass, which can be accelerated or decelerated, a photon is born into motion at c and continues at that speed until it is absorbed or interacts with matter. This unwavering commitment to a single speed underscores the unique role of light as the universe's ultimate messenger and its intrinsic connection to the fabric of space-time. It is a silent law, ensuring that light's journey is always at the swiftest possible pace, delivering information across vast distances with unparalleled efficiency. The very nature of light is defined by its ceaseless, unhurried rush, a perpetual state of graceful flight through the boundless expanse, confirming its singular and unchangeable role in the cosmos. This constant velocity is a testament to the elegant simplicity that underlies the fundamental principles of the universe, a continuous and serene flow of energy. The profound implication of a photon having no rest mass extends further. If a photon could theoretically be at rest, it would effectively possess zero energy. This state, however, is not possible for a particle of light. The energy of a photon is directly linked to its frequency and, by extension, its motion. A photon's very existence is defined by its vibrant oscillation and its ceaseless propagation. If it were to become stationary, it would lose its inherent frequency and thus its energy, effectively ceasing to exist as a particle of light. This is a crucial distinction from particles with mass, which can possess rest energy even when stationary, as described by Einstein's famous equation, E equals mc squared. For a photon, m, mass, is zero, meaning its energy, E, is entirely derived from its momentum and frequency, which are products of its motion. Thus, the idea of a still photon is a contradiction in terms, a conceptual impossibility within the framework of modern physics. It is a serene reminder that light is fundamentally a dynamic entity, a pure expression of energy in motion, forever bound to its graceful journey through the cosmos. This inherent dynamism ensures that light remains an active, vibrant force, perpetually illuminating the universe without the possibility of repose, a timeless dance of energy. Moving from the individual photon to more complex quantum phenomena, we encounter quantum entanglement, a truly mysterious and profound connection between particles. While this effect might appear to connect particles instantaneously across vast distances, it does not, in fact, allow information to travel faster than light. Quantum entanglement involves two or more particles becoming linked in such a way that the quantum state of one particle cannot be described independently of the others, even when they are separated by immense cosmic gulfs. When one entangled particle is measured, its partner instantly assumes a correlated state, regardless of the distance between them. This seemingly instantaneous influence once puzzled even Einstein, who famously called it spooky action at a distance. However, careful scientific understanding clarifies that this remarkable correlation does not violate the cosmic speed limit. The information about the measured state is not being sent from one particle to another in a way that could carry a message. Instead, the particles are part of a single unified quantum system, and their states are decided together at the moment of measurement. It is a subtle, non-dramatic truth that preserves the fundamental laws of relativity, ensuring that the universe's speed limit for information remains intact, a tranquil testament to the elegant consistency of its physical principles. To elaborate on why quantum entanglement cannot be harnessed for superluminal communication, despite the instantaneous influence of one particle's measurement on its partner, we must consider the inherent randomness of quantum mechanics. When you measure an entangled particle, the outcome is fundamentally probabilistic. You cannot predetermine what that outcome will be. It's like flipping a coin, but the outcome of your coin flip instantly determines the outcome of your entangled partner's coin flip, no matter how far away they are. However, you cannot choose the outcome of your flip to send a specific message. Since the result of your measurement is random, you cannot encode a meaningful message into the state of your particle to be instantly received by your distant partner. To extract any information, the distant observer would still need to compare their measurement results with yours, and that comparison requires traditional, light-speed limited communication. Therefore, while the correlation itself is instantaneous, the transfer of usable information remains bound by the speed of light. This subtle constraint ensures that the universe maintains its causal order, preventing any violation of the cosmic speed limit and preserving the serene integrity of space-time. It is a beautiful example of how the mysteries of quantum mechanics harmonize with the principles of relativity, revealing a cosmos that is both deeply interconnected and subtly constrained, a peaceful balance of profound phenomena. In a truly remarkable feat of experimental physics, scientists have managed to effectively stop light for brief periods by trapping photons within ultra-cold atomic clouds. This astonishing achievement does not, however, imply a violation of the speed of light, but rather a clever manipulation of light's energy and its interaction with matter. Imagine a delicate, wispy cloud of atoms, cooled to temperatures just a tiny fraction above absolute zero, creating an exquisitely sensitive environment. In these conditions, researchers can guide a pulse of light into the cloud, where the photons interact with the atoms in such a way that their energy is temporarily imprinted onto the atomic states. The light itself, in its photon form, essentially vanishes, but its information and energy are carefully stored within the collective quantum state of the atomic cloud. This is not light ceasing to move, but its energy being gently converted and held in a different form, a serene and controlled transformation. This pioneering work opens new avenues for quantum computing and communication, allowing for the temporary storage and retrieval of light-based information. It is a tranquil demonstration of humanity's growing mastery over the subtle forces of the quantum world, showing how light's energy can be patiently paused and then gracefully resumed on its luminous journey. This process of stopping light involves a precise and elegant conversion of the photon's energy into an atomic excitation. When the light pulse enters the ultra-cold atomic cloud, the photons do not simply halt in place. Instead, their energy and quantum information are transferred to the electrons within the atoms, exciting them to higher energy levels. This effectively transforms the light's energy into a collective, coherent excitation within the atomic ensemble. The original photons are absorbed, and their luminous presence is temporarily suspended. The atomic cloud then holds this stored energy, like a gentle memory of the light that once passed through it. Later, under carefully controlled conditions, this atomic excitation can be precisely stimulated, causing the atoms to de-excite and re-emit the light, essentially reconstructing the original light pulse. This re-emission occurs with the same properties and characteristics as the initial light, allowing the stored information to be retrieved. It is a testament to the seamless interchangeability of energy between light and matter, a beautiful and intricate dance at the quantum level. This controlled conversion and re-emission underscore the profound connection between light and the quantum states of atoms, revealing a universe where energy can gracefully transform and reappear, a silent and elegant process that expands our understanding of light's versatile nature. As we continue our tranquil exploration of light's profound influence, we now turn to one of the most astonishing consequences of its constant speed, the warping of time and space themselves, as predicted by Albert Einstein's special theory of relativity. Imagine an object possessing mass, such as a spacecraft or even a tiny subatomic particle, embarking on a journey through the cosmos and gracefully accelerating to speeds that approach the speed of light. As this object draws closer to that ultimate cosmic velocity, a remarkable phenomenon begins to unfold. Time for that object slows down relative to a stationary observer. This captivating effect is known as time dilation. It means that clocks aboard the swiftly moving object would tick more slowly, and all biological and physical processes within it would proceed at a more leisurely pace compared to identical processes observed from a stationary vantage point. This is not an illusion or a trick of perception, but a fundamental alteration in the flow of time itself, a serene and undeniable consequence of motion at relativistic speeds. The faster the object moves, the more pronounced this gentle stretching of time becomes, revealing a universe where time is not an absolute, unyielding river, but a flexible stream responsive to the velocity of its inhabitants, a profound and elegant testament to the interconnectedness of motion and temporal progression. This effect ensures that the universe maintains its internal consistency, even as different observers perceive time's passage differently, a quiet harmony within the grand cosmic design. This fascinating phenomenon of time dilation is not merely a theoretical construct or a subject of abstract contemplation. It is a direct and experimentally verified consequence of special relativity. Countless experiments, from the precise measurements of subatomic particles in accelerators to the careful synchronization of atomic clocks flown around the world, have confirmed its reality with astonishing accuracy. For instance, unstable particles known as muons, which have very short lifespans when at rest, are observed to live significantly longer when traveling at speeds close to light speed, exactly as predicted by time dilation. These meticulous observations have profoundly altered our perception of time, transforming it from a universal, unchanging constant into a dynamic dimension that is intricately interwoven with motion and space. It reveals that the flow of moments is not an absolute, unhurried river, but rather a stream whose pace can gently vary, depending on one's velocity through the cosmos. This experimental validation ensures that time dilation is a fundamental truth of our physical reality, reshaping our understanding of the very fabric of existence and the subtle ways in which the universe expresses its deep, elegant laws. The verification of this effect stands as a serene triumph of scientific inquiry, allowing us to glimpse the profound and beautiful flexibility of space-time itself, a quiet testament to Einstein's enduring genius. In an exquisite complementary dance with time dilation, another remarkable relativistic effect emerges as an object approaches the speed of light. From the perspective of a stationary observer, the length of the moving object appears to contract in the direction of its motion. This captivating phenomenon is known as length contraction. Imagine a long, slender spacecraft gracefully accelerating to speeds close to c. To an observer watching from a stationary planet, that spacecraft would appear to become subtly shorter along its direction of travel. Like time dilation, this is not an optical illusion, but a genuine consequence of the object's motion through space-time. The extent of this contraction becomes more pronounced as the object's speed increases, growing significant only at extreme velocities. The dimensions perpendicular to the direction of motion, however, remain unchanged, creating a serene and precise distortion of shape. This phenomenon, along with time dilation, illustrates how the very geometry of space and the passage of time are intimately linked and responsive to an observer's relative motion. It is a profound and elegant aspect of special relativity, revealing that our perception of physical dimensions is not absolute, but subtly interwoven with the dynamics of motion, a quiet testament to the flexible and interconnected nature of the cosmic fabric. This fascinating phenomenon, length contraction, stands as a complementary effect to time dilation, and it too becomes significant only at the most extreme speeds, those drawing intimately close to the speed of light. In our everyday experience, where velocities are minuscule compared to c, these contractions are utterly imperceptible. A car traveling at highway speeds or even a high-speed jet experiences a length contraction so infinitesimally small that it is beyond any possibility of measurement. However, for particles accelerated in colossal machines, or for hypothetical spacecraft reaching a substantial fraction of light speed, the effect becomes quite real and measurable. This means that for observers moving at different velocities, their measurements of an object's length will genuinely differ, yet both will be correct within their respective frames of reference. This elegant interplay of relative perception ensures the consistency of physical laws across all inertial frames, preserving the serene harmony of the cosmos. It is a subtle, unhurried distortion of spatial dimensions, a quiet whisper of the universe's inherent flexibility, reminding us that our everyday notions of fixed length and unchanging space are but approximations that hold true only in the gentle realm of low velocities, far removed from the profound dynamics near the cosmic speed limit. Pushing these relativistic concepts to their theoretical limit, if an object with mass could somehow achieve the impossible feat of traveling, i.e., the speed of light, the consequences would be truly profound and mind-bending. For such an object, time would effectively cease to flow. It would experience no passage of moments, its internal clocks entirely halted, and its biological processes frozen in an eternal instant. Simultaneously, its length in the direction of motion would contract to zero, effectively disappearing into a two-dimensional plane. This theoretical scenario underscores why only massless particles, like photons, can travel at sea in a vacuum. Any object with mass would require an infinite amount of energy to reach such a speed and would experience these extreme distortions of space and time. This ultimate theoretical boundary reveals the profound and unyielding nature of the cosmic speed limit, not as a mere barrier, but as an intrinsic property of the universe that gracefully shapes the very existence of mass and energy. It is a serene contemplation of the absolute limits of physical reality, illustrating the elegant consistency of Einstein's theories and the fundamental distinction between particles with and without mass, a quiet testament to the universe's ultimate design. It is crucial to emphasize that these mind-bending relativistic effects, such as time dilation and length contraction, are only noticeable at speeds very close to the speed of light. These are velocities far beyond our everyday experience, rendering these phenomena utterly imperceptible in our routine lives. When we walk, drive, or even fly in an airplane, our speeds are so infinitesimally small compared to c that the relativistic distortions of time and space are negligible, amounting to fractions of a nanosecond or microscopic changes in length. Our classical understanding of fixed time and absolute space remains perfectly valid and practical for the vast majority of human endeavors. It is only when particles are accelerated in colossal scientific instruments, or when considering hypothetical interstellar travel at immense fractions of light speed, that these effects become significant and measurable. This means that the universe, in its gentle wisdom, allows us to experience a seemingly stable and intuitive reality for most of our lives, while reserving its more profound and flexible nature for the extreme realms of cosmic velocity. It is a tranquil reminder that our everyday perceptions are but a limited view of a much grander, more dynamic cosmic canvas, where time and space are subtly yet beautifully responsive to motion, a serene whisper of the universe's deeper truths. Despite these effects being largely imperceptible in daily life, the precision of modern science allows us to measure even the most minute relativistic changes. For instance, even astronauts aboard the International Space Station, or ISS, experience tiny, measurable amounts of time dilation due to their high orbital speed. Though the ISS orbits Earth at an impressive speed of approximately 17,500 miles per hour, this is still a tiny fraction of the speed of light. Nevertheless, thanks to incredibly precise atomic clocks, scientists can detect that time for astronauts on the ISS runs ever so slightly slower than for those of us on Earth's surface. This difference amounts to only fractions of a second over an entire year, but it is a consistent and predictable effect, perfectly aligning with Einstein's predictions. These delicate measurements provide yet another compelling confirmation of special relativity, demonstrating that time dilation is not just a theoretical concept for extreme scenarios, but a subtle, pervasive reality that gently influences even our relatively modest journeys through space. It is a tranquil testament to the universe's intricate precision, revealing that even the smallest movements at high velocity leave their gentle imprint on the flow of time, connecting our human endeavors directly to the profound laws that govern the cosmos, a quiet harmony of physics on both grand and subtle scales. Our serene journey through the cosmos now leads us to one of the most iconic and deeply profound expressions of universal physics, Albert. This elegant mathematical statement, renowned across the globe, directly links the fundamental concepts of mass and energy, seamlessly weaving them together through deceptively simple formula, yet its implications are colossal, revealing an intrinsic equivalence that the E represents energy, the M stands for mass, and c is, of course, the constant speed of light in a vacuum. This equation suggests that mass is simply a highly concentrated form of energy, and conversely, energy itself possesses a subtle form of mass. It establishes a fundamental bridge between these two seemingly distinct properties of the universe, demonstrating that they are merely different manifestations of the same underlying cosmic essence. This profound relationship clarifies that the universe is not composed of separate entities of mass and energy, but rather a unified, dynamic fabric where one can gracefully transform into the other, guided by the constant and precise factor of light's speed, a silent, enduring testament to the interconnectedness of all physical phenomena. This intimate link provides a tranquil framework for understanding the subtle conversions that constantly occur within the heart of stars and across the vast emptiness of space, painting a picture of cosmic unity. This celebrated equation reveals a truly astonishing cosmic truth. A remarkably small amount of mass can be converted into an absolutely enormous quantity of energy. Conversely, though less frequently observed in our everyday experience, energy itself can be transformed into mass. This profound interchangeability underscores the deep unity between these two fundamental properties of the universe. When mass is converted into energy, it is not a violent destruction, but rather a serene unfolding, a release of the immense inherent energy that was previously bound within the structure of matter. Imagine a tiny, almost imperceptible particle of matter containing within it a vast, latent reservoir of power, patiently waiting to be unfurled into the cosmos. This conversion process is the engine behind many of the universe's most majestic phenomena, from the steady glow of distant stars to the subtle processes that shape the very elements around us. The reverse transformation, where pure energy condenses into mass, is a more elusive process, typically occurring in high-energy particle interactions in the early universe or within powerful cosmic accelerators. This delicate balance, this constant potential for transformation, highlights the dynamic and fluid nature of cosmic existence, where mass and energy are perpetually engaged in a graceful, silent dance of interchange. It is a tranquil revelation, showcasing the universe's profound capacity for self-renewal and transformation, ensuring that nothing is ever truly lost, merely transformed into another elegant form of being, a continuous cycle of cosmic becoming. The sheer power inherent in this mass energy conversion is profoundly emphasized by the c² term within Einstein's equation. This component, representing the speed of light multiplied by itself, is not merely a numerical factor. It is the colossal amplification engine that highlights the immense energy contained within even tiny amounts of mass. Since the speed of light, c, is already an extraordinarily vast number, nearly 300 million meters per second, squaring it yields an astronomically larger figure. This enormous multiplier reveals why even a minuscule quantity of matter holds such a staggering potential for energy release. Imagine a gentle whisper that, when squared, becomes a roaring symphony. Similarly, c² transforms modest mass into an incredible energetic output. It is this vast scaling factor that makes nuclear processes so potent, unlocking energies that dwarf those released by ordinary chemical reactions. The presence of c² in the equation underscores that mass is not just inert matter, but a highly concentrated, dormant form of energy, patiently awaiting its transformation. This term is a silent testament to the universe's inherent power, revealing that the very fabric of existence, even in its most subtle forms, harbors an immense energetic potential, a tranquil and constant hum of latent cosmic force. Waiting for the gentle nudge of transformation, this profound mass energy conversion is perfectly and majestically demonstrated by nuclear reactions, which are the very heartbeats of cosmic power. Consider the serene, unceasing radiance of our own sun. In its core, a gentle process of nuclear fusion continuously occurs, where hydrogen atoms are slowly, patiently converted into helium. In each of these fusion events, a tiny fraction of the original mass of the hydrogen is not lost, but rather transformed into an enormous burst of energy, primarily in the form of light and heat. This steady, controlled release of energy is what allows the sun to shine for billions of years, providing the warmth and light essential for life on Earth. On a different scale, though still governed by the same principle, atomic explosions also demonstrate this conversion, albeit in a swift and intense manner. Here, the rapid fission or fusion of atomic nuclei releases a colossal amount of energy from a small mass, a dramatic yet natural unfolding of E equals mc squared. These events, whether the long tranquil burn of a star or the fleeting burst of an atomic reaction, are tangible proof of the deep intrinsic link between mass and energy, showcasing the universe's power to transform one into the other with elegant precision. Indeed, since the speed of light, c, is such a colossal number, its square, c squared, profoundly emphasizes the extraordinary power of this conversion process. The magnitude of this multiplier is what gives nuclear physics its immense significance. If c were a smaller number, the energy released from a given amount of mass would be far less, and the universe would be a very different place, perhaps less vibrant, less energetic. But because c is so immense, the energy equivalent of even a tiny particle of matter is staggering. This mathematical reality means that the universe holds vast reservoirs of energy locked within its matter, patiently waiting for the right conditions to be released. It is this immense factor of c squared that allows stars to shine for eons, fuels the processes that forge heavier elements, and ultimately provides the energetic backdrop for all cosmic evolution. The colossal nature of c squared is therefore not just a numerical detail, but a fundamental aspect of cosmic design, ensuring that the universe is imbued with immense potential, capable of both gentle, sustained radiance and swift, powerful transformations, a silent testament to the profound energetic richness of existence. This fundamental relationship, E equals mc squared, underpins our entire understanding of a vast array of cosmic phenomena. It is not merely an isolated equation, but a foundational pillar that supports our comprehension of stellar processes. It explains how stars ignite, how they maintain their long, luminous lives through the gentle fusion of elements, and how they eventually return their enriched material to the cosmos in a final burst of radiance. Beyond stars, it is crucial to particle physics, shedding light on how subatomic particles interact, transform, and emerge from pure energy in high-energy collisions. Furthermore, this equation is essential to understanding the very structure of matter itself, revealing that the bonds holding atomic nuclei together contain immense energy, and that mass is not an inert property, but a dynamic manifestation of concentrated energy. It provides a coherent framework for interpreting the universe's most energetic events and the most subtle interactions, offering a consistent and elegant description of how mass and energy flow and transform throughout the cosmos. This foundational principle is a tranquil guide, illuminating the intricate workings of the universe from its smallest particles to its grandest structures, a quiet revelation of cosmic interconnectedness. In its most elegant and concise form, Einstein's equation profoundly shows that mass is a highly concentrated form of energy. Imagine energy as a vast ethereal ocean. Mass, then, is like a drop of that ocean that has been gently condensed, becoming incredibly dense and potent. It is energy in a state of quiet repose, held within the structure of matter. Conversely, the equation also reveals that, while photons, as pure energy, have no rest mass, they do possess momentum and contribute to the gravitational field, acting as if they have an equivalent mass when in motion. This means that even a beam of light, while massless in the traditional sense, can exert a gentle gravitational pull and be influenced by gravity, as we discussed earlier. This reciprocal relationship dissolves the classical distinction between mass and energy, presenting them as two facets of the same fundamental cosmic coin. It is a beautiful, serene truth that speaks to the deep unity of all physical phenomena, revealing that the universe is ultimately composed of a single, flowing essence that can manifest as either tangible matter or radiant energy, forever linked by the unwavering speed of light, a gentle, continuous dance of cosmic transformation and balance. Our journey through the cosmos now takes a reflective turn, guiding us back through the annals of human curiosity to explore the historical quest to understand the speed of light. For centuries, the nature of light remained a profound mystery, with many believing it to be instantaneous, an omnipresent illumination. The earliest known attempt to measure the speed of light, a pioneering endeavor that marked the beginning of this scientific quest, was undertaken by the brilliant Italian polymath Galileo Galilei in the early 1600s. This was a time long before the advent of modern instruments, when scientific inquiry relied on ingenuity and observation rather than sophisticated technology. Galileo, ever the innovator, sought to apply experimental methods to questions previously confined to philosophical debate. His quiet, patient efforts laid the groundwork for future generations of scientists who would gradually unravel the secrets of light's swift passage. This early attempt, though rudimentary by today's standards, represented a crucial shift in thinking, moving from abstract speculation to empirical investigation, a gentle awakening to the measurable realities of the physical world. It was a serene beginning to a long and profound scientific journey, setting the stage for humanity's gradual understanding of light's true nature. Galileo's experimental setup, a testament to his inventive spirit, involved two individuals equipped with lanterns positioned on distant hills. The first person would uncover their lantern, and upon seeing its light, the second person would immediately uncover their own. The first person would then attempt to measure the time elapsed between uncovering their lantern and seeing the light from the second lantern. The idea was that if light had a finite speed, a measurable delay would be observed. However, the distances involved, while significant for the technology of the time, were far too small for Galileo's simple method to detect the astonishingly swift travel of light. His ingenious, yet constrained experiment could only conclude that light was incredibly fast, if not effectively instantaneous from a human perspective. The limitations of his instruments and the immense speed of light meant that any delay was far too brief for the human eye and rudimentary timing devices to register. This early endeavor, though not yielding a precise numerical value, was a crucial conceptual step, firmly establishing the idea that light might indeed have a finite velocity and could, in principle, be measured. It was a quiet, patient inquiry that, while not providing the answer, beautifully framed the question for future generations, inviting them to refine the methods and eventually unveil light's true speed. The first truly successful quantitative measurement of the speed of light, marking a significant milestone in scientific history, was achieved by the Danish astronomer Ole Rømer in 1676. Working at the Royal Observatory in Paris, Rømer was observing the celestial dance of Jupiter and its moons. Unlike Galileo's terrestrial experiments, Rømer leveraged the vast distances of the solar system as his laboratory, employing astronomical observations to unveil light's hidden velocity. His meticulous and patient work, conducted with the relatively simple telescopes of his era, revealed a profound cosmic truth that had eluded scientists for centuries. It was a quiet, yet monumental leap in human understanding, moving from mere speculation to a precise, verifiable measurement, forever altering our perception of light's fundamental nature. Rømer's ingenuity demonstrated that the universe itself could serve as a grand clock, its celestial rhythms providing the subtle clues needed to unravel one of its deepest secrets. His groundbreaking discovery marked the transition from qualitative observation to quantitative understanding, laying the foundation for all subsequent measurements and theories regarding the speed of light, a tranquil testament to the power of careful astronomical inquiry. Rømer's ingenious method for deducing light's finite speed involved patiently observing slight variations in the timing of Jupiter's moon Io's eclipses. Io, one of Jupiter's 4 largest moons, is regularly eclipsed as it passes into Jupiter's shadow. Rømer noticed that the observed timing of these eclipses seemed to vary depending on Earth's position in its orbit around the Sun. When Earth was moving away from Jupiter, the eclipses appeared to occur later than predicted, as if the light had to travel a greater distance. Conversely, when Earth was moving towards Jupiter, the eclipses appeared to happen earlier than expected. Rømer correctly hypothesized that these discrepancies were not due to irregularities in Io's orbit, but rather to the finite time it took for light to travel the varying distances between Earth and Jupiter. As the distance between the two planets increased, light had further to go, causing a delay. As the distance decreased, the light arrived sooner. From these subtle, periodic delays, Rømer was able to calculate a value for the speed of light, which, though not perfectly accurate by modern standards, was remarkably close and undeniably demonstrated that light travels at a measurable finite velocity. It was a profound and elegant deduction, transforming seemingly minor astronomical anomalies into a monumental discovery, a silent whisper from the outer solar system revealing light's true pace. While Rømer's work provided the first astronomical measurement, the first successful terrestrial measurement of the speed of light, conducted entirely on Earth, was performed by the French physicist Hippolyte Fizeau in 1849. Fizeau's ingenious experiment brought the vastness of light's journey down to a human scale, using a clever mechanical setup. His method involved a rapidly rotating toothed wheel and a distant mirror, positioned several kilometers away. A beam of light was passed through the gaps in the spinning wheel, traveled to the distant mirror, reflected back, and passed through the same wheel again. By precisely controlling the speed of the rotating wheel, Fizeau could adjust it so that the returning light beam either passed through an adjacent gap or was blocked by a tooth. The key was to measure the exact rotational speed of the wheel at which the light, having traveled to the mirror and back, was just blocked by the next tooth. Knowing the distance to the mirror and the rotational speed of the wheel, Fizeau could calculate the time it took for the light to complete its round trip, and thus determine its speed. This elegant and precise experiment provided a direct, earthbound confirmation of light's finite velocity, laying the groundwork for even more accurate measurements in the years to come, a tranquil triumph of human ingenuity in the controlled environment of a laboratory. As the 19th century drew to a close, Albert Michelson and Edward Morley embarked on a series of famous experiments that, while failing in their initial objective, inadvertently paved the way for one of the most significant revolutions in physics. Their primary goal was to detect a hypothetical medium known as the luminiferous ether, through which light was thought to propagate. At the time, physicists believed that if light were a wave, it must, like sound waves in air or water waves in water, require a medium to travel through. The ether was imagined as an invisible, omnipresent substance filling all of space, serving as light's carrier. Michelson and Morley designed an incredibly precise interferometer to detect Earth's motion through this stationary ether. They hypothesized that light traveling in the direction of Earth's motion through the ether would have a slightly different speed than light traveling perpendicular to it, creating a detectable interference pattern. Their meticulous work aimed to capture this subtle difference, which would confirm the ether's existence. The serene precision of their apparatus pushed the boundaries of experimental measurement, showcasing the dedication of scientists to unraveling the fundamental nature of light's journey. Despite the extreme precision and careful execution of their experiments, Michelson and Morley found no evidence of such an ether. Repeated measurements, taken at different times of the year as Earth changed its direction of motion through space, consistently yielded a null result. The speed of light always appeared to be the same, regardless of Earth's movement. This unexpected outcome, the persistent absence of the hypothesized ether, was deeply perplexing to the scientific community of the late 1800s. It directly contradicted the prevailing theories of how light waves behaved and presented a profound challenge to classical physics. However, far from being a failure, their experiments were crucial in paving the way for Albert Einstein's revolutionary theories of relativity. The unwavering constancy of the speed of light, as demonstrated by Michelson and Morley, became a foundational premise for Einstein's special relativity, which elegantly explained why no ether was necessary and why light speed is indeed invariant for all observers. Their meticulous and patient work, initially intended to confirm an existing theory, instead gently guided physics towards a completely new and profound understanding of space, time, and the very nature of light, a silent, yet monumental contribution that reshaped our cosmic perspective forever. From the philosophical inquiries of Galileo and the astronomical observations of Rømer to the foundational experiments of Michelson and Morley, humanity's evolving understanding of the speed of light has paved the way for remarkable modern applications. Indeed, the speed of light is not merely an abstract cosmic constant. It is absolutely fundamental to the operation of the Global Positioning System, or GPS, technology, allowing it to function with remarkable accuracy. This ubiquitous system, which silently guides our journeys and helps us navigate our world, relies entirely on the precise and unwavering velocity of light. Without the consistent and predictable speed of light, the intricate calculations that pinpoint our location on Earth would be impossible. Imagine a tranquil network of orbiting satellites, each a silent beacon in the sky, diligently broadcasting signals that race through the vacuum of space at sea. This complex dance of light and time is what enables GPS receivers in our phones and vehicles to determine our position with serene precision, transforming an abstract physical constant into a practical, everyday utility. It is a testament to how deeply interwoven the fundamental laws of the cosmos are, with the technological advancements that shape our modern lives, a quiet harmony between the vastness of space and the intricacies of human innovation, gently guiding our way across the planet. To understand how GPS achieves its remarkable accuracy, we delve deeper into the role of light's speed. GPS satellites, orbiting high above Earth, continuously send out radio signals, which are a form of electromagnetic radiation and thus travel at the speed of light. Each signal contains precise timing information. When a GPS receiver on Earth picks up these signals from multiple satellites, it measures the exact time it took for each signal to travel from its satellite to the receiver. Because the speed of light is known with such extraordinary precision, the time taken for the signal's journey directly determines the distance to each satellite. By combining these distance measurements from at least 4 different satellites, the receiver can triangulate its precise location on Earth with serene accuracy. This elegant system, built upon the unyielding constancy of light's speed, allows for navigation that guides ships across vast oceans, helps aircraft land safely, and even assists rescue teams in emergencies. It is a quiet testament to the practical power of a fundamental cosmic constant, transforming the swift flow of photons into a reliable guide for human endeavors, a continuous, subtle symphony of signals that quietly shape our modern world, ensuring that we always know our place. Beyond its practical applications in navigation, precise measurements of the speed of light hold an even more fundamental significance. They are used to define the meter in the international system of units, ensuring a universal and unwavering standard for length. For centuries, the definition of a meter evolved, initially based on a fraction of Earth's circumference, then on a physical platinum iridium bar. However, these standards were susceptible to environmental changes or could not be replicated with absolute precision. The advent of highly accurate measurements of light speed provided an opportunity for a more stable and universal definition. By linking length directly to the speed of light and time, scientists established a standard that is intrinsically tied to a fundamental constant of the universe, rather than a perishable artifact. This elegant redefinition ensures that the meter is consistent across all laboratories, and indeed throughout the cosmos, providing a truly universal benchmark for spatial measurement. It is a tranquil example of how human ingenuity aligns with cosmic principles, creating a system of measurement that is both profoundly practical and beautifully consistent with the underlying laws of nature, a silent pillar of scientific precision. To be exquisitely precise, 1 meter is currently defined as the exact distance light travels in a vacuum in 1/8 of a second. This incredibly specific and fractional duration highlights the extraordinary precision with which the speed of light is known and utilized. Instead of defining the speed of light based on a pre-existing meter, the process has been reversed. The meter is now defined by the speed of light. This means that the value of c is no longer an experimentally determined quantity that might be refined over time. It is now a fixed, defined constant. Any future improvements in measuring the speed of light would instead lead to a more precise determination of the length of a second, or rather, how many meters light travels in a second. This elegant redefinition of the meter provides a foundational standard for all physical measurements, ensuring unparalleled accuracy and consistency in scientific research and technological development worldwide. It is a testament to the profound relationship between light, time, and space, illustrating how a universal constant can anchor our most fundamental units of measurement, providing a serene and unchanging reference in the ever-unfolding cosmic story, a quiet harmony of physical definitions. Our profound understanding of the speed of light also enables astronomers to perform remarkable feats of cosmic measurement. Laser ranging experiments, for instance, utilize the unwavering velocity of light to measure distances to the Moon and other celestial bodies with exquisite accuracy. This technique involves firing powerful laser pulses from Earth towards retroreflectors placed on the Moon by Apollo missions. The laser light travels to the Moon, reflects off these special mirrors, and then returns to Earth. By precisely measuring the round-trip travel time of these light pulses and knowing the exact speed of light, scientists can calculate the distance to the Moon with astonishing precision, down to mere centimeters. This method is also employed for measuring distances to orbiting satellites and even to some planetary probes. It is a serene and elegant application of fundamental physics, transforming light's swift journey into a precise ruler for the vastness of space. These experiments not only refine our understanding of lunar dynamics and Earth's rotation, but also offer compelling evidence of across astronomical distances, a tranquil dance of light and reflection across the cosmic expanse, unveiling the subtle geometry of our celestial neighborhood. Furthermore, the speed of light is absolutely crucial for understanding the intricate workings of fiber optic communication, a technology that forms the very backbone of our modern information age. In fiber optic systems, information is encoded onto pulses of light, which then travel through incredibly thin strands of glass or plastic fiber. These light signals carry vast amounts of data, from internet traffic and phone calls to streaming video, across continents and under oceans, at speeds approaching the speed of light. While light does slow down slightly when passing through the glass fiber compared to a vacuum, its velocity within the fiber is still extraordinarily high, enabling rapid and efficient data transmission across immense distances. The ability to precisely control and guide these light signals, leveraging their speed and purity, has revolutionized global communication, connecting people and cultures across the planet with almost instantaneous information exchange. It is a testament to the elegant practicality of light's properties, transforming its ethereal nature into a vital conduit for human connection and knowledge, a quiet network of luminous threads weaving together the modern world, making the vastness of Earth feel intimately connected, a serene flow of digital information. Finally, and perhaps most importantly for our cosmic understanding, astronomers routinely use the speed of light in their calculations to determine the actual sizes, distances, and luminosities of countless cosmic objects. Because light takes time to travel, observing a distant galaxy means seeing it as it was in the past. By measuring the redshift of light from these galaxies, which indicates how much the universe has expanded since that light was emitted, astronomers can calculate their distances. With distance known, the apparent brightness of a celestial object can be used to determine its true luminosity, and its apparent size can reveal its actual physical dimensions. The speed of light acts as a cosmic ruler and a cosmic clock, allowing scientists to reconstruct the universe's vast history and its intricate structure. Without a precise understanding of c, our maps of the cosmos would be distorted, and our timelines of cosmic evolution would be inaccurate. It is a fundamental tool, enabling us to unravel the grand narrative of the universe, from the birth of stars to the formation of galaxies, painting a comprehensive and awe-inspiring picture of the cosmos. a tranquil and patient process of cosmic cartography, revealing the silent, majestic unfolding of space and time. As we continue our tranquil journey through the cosmos, we encounter a concept that profoundly intertwines with the speed of light, the universe's own majestic expansion. This grand unfolding of space itself leads to some truly intriguing observations. Scientists have discovered that the universe is expanding, and as a result, very distant galaxies are receding from us at speeds that, at first glance, can appear to exceed the speed of light. This observation might seem to challenge the fundamental cosmic speed limit, but it is a subtle phenomenon that requires a deeper understanding. Imagine the cosmos as a vast, gentle balloon slowly inflating. The dots on its surface move farther apart, not because they are crawling across the surface, but because the surface itself is stretching. This cosmic expansion is not a movement through space, but rather an increase in the space between objects. It's a serene, unhurried growth that affects the very fabric of the universe, causing distant celestial bodies to drift apart with increasing velocity. This graceful, continuous expansion ensures that the cosmic landscape is never static, but always in a state of subtle, dynamic change, revealing a universe that is both expanding and perpetually adhering to its intrinsic speed limits within localized regions. This apparent superluminal recession is a testament to the profound flexibility of space-time itself. This apparent superluminal speed of distant galaxies is not a violation of the cosmic speed limit, but rather a consequence of the expansion of space itself, not the galaxies moving through existing space faster than light. The distinction is crucial for understanding the elegant consistency of physical laws. Within a local region of space, such as our solar system or even our galaxy, objects are bound by gravity and move through space at speeds well below c. However, the space between these bound systems is stretching, carrying them farther apart. Imagine drawing dots on an unbaked loaf of bread. As the bread bakes and expands, the dots move away from each other. They aren't traveling across the bread faster than any internal speed limit of the dough. Rather, the dough itself is growing, increasing the distances between the dots. Similarly, galaxies are largely stationary relative to their local space, but the intervening space grows, making them appear to recede at extraordinary velocities. This serene cosmic stretch is a gradual, continuous process that affects the entire universe, influencing the paths of light and the perception of distance, a quiet, unhurried unfolding of the cosmic fabric. Universe maintains its fundamental laws even while undergoing a grand, overarching transformation, a peaceful harmony of motion and expansion that gently guides the celestial dance. To maintain clarity and ensure the integrity of Einstein's principles, it is vital to emphasize that locally, within our own galaxy or solar system, nothing travels faster than light through space. The cosmic speed limit of c remains an absolute and unbreakable barrier for any object with mass moving within a defined region of space-time. Our understanding of this local constraint is supported by countless experiments and observations, from particle accelerators to the behavior of cosmic rays. Within the gravitational embrace of our Milky Way galaxy, stars, gas clouds, and even our solar system move at speeds far below light speed. The same applies within our solar system, where planets orbit the Sun at velocities that are minuscule compared to c. Any signal or object attempting to traverse these local distances is strictly bound by light's unwavering speed. This local adherence to the cosmic speed limit ensures the principle of causality, meaning that cause always precedes effect, maintaining the serene order and predictability of physical interactions in our immediate cosmic neighborhood. It is a tranquil assurance that, despite the grand expansion of the universe, the fundamental laws governing motion and information transfer remain consistent and inviolable within our immediate experience, a quiet testament to the enduring elegance of cosmic physics. The profound interplay between the speed of light and the universe's expansion helps to define a crucial concept in cosmology: the cosmic horizon. This horizon, which delineates the limit of the observable universe, is determined by how far light has traveled since the Big Bang. Since the universe has a finite age, approximately 13.8 billion years, there is a maximum distance from which light could have possibly reached us. This boundary is not a physical edge in space, but rather a temporal one, a gentle limit to our perception. Imagine a cosmic lighthouse that began shining at the very beginning of time. The cosmic horizon marks the farthest point from which its light has had enough time to reach our vantage point. As light travels across the expanding universe, it stretches and ages, eventually reaching us as faint, red-shifted signals. This horizon defines the vast, spherical region of space containing all the galaxies, stars, and matter whose light has had the opportunity to complete its long, unhurried journey to Earth. It is a serene boundary, continually expanding as the universe ages, but always representing the limit of what we can currently witness, a quiet testament to the profound relationship between light's journey and cosmic time. A direct and profound consequence of this cosmic horizon is that light from objects beyond this boundary has not yet had sufficient time to reach us, making them currently invisible to our telescopes. These distant realms are not empty. They are filled with countless more galaxies and cosmic structures, just like those within our observable universe. However, because the light they have emitted has not yet completed its immense journey across the expanding cosmic canvas, they remain forever beyond our current visual reach. It's like standing in a vast, ancient forest. You can only see the trees whose light has had time to reach your eyes, while those further away are still shrouded in the temporal mists of distance. As the universe continues to age and expand, this cosmic horizon slowly recedes, gradually unveiling new, more distant galaxies to our telescopes. Yet, due to the accelerating expansion of space, some regions may remain forever beyond our observational grasp, their light destined to never reach us. This gentle limitation reminds us of the profound humility inherent in cosmic exploration, acknowledging that the universe is far vaster and holds many more hidden wonders than what we can currently perceive. A tranquil and enduring mystery that invites future generations to continue the patient quest for knowledge. The expansion of space itself has another profound and beautiful effect on the light traveling through it, causing a phenomenon known as cosmological redshift. As light embarks on its long, unhurried journey across the vast and stretching fabric of the universe, the space between the emitting galaxy and our telescopes gently expands. This expansion stretches the very wavelength of the light waves, causing them to lengthen. Longer wavelengths correspond to the redder end of the electromagnetic spectrum. Imagine a rubber band with a wave drawn on it. As the rubber band is stretched, the wave on it also lengthens. Similarly, light from distant galaxies appears redder to us than it was when it was originally emitted. This is not due to the galaxies themselves moving through space at high speeds, as in the Doppler effect, but rather due to the expansion of the intervening space. It is a subtle, continuous stretching that subtly shifts the color of ancient starlight, transforming its spectral signature into a cosmic odometer. This elegant phenomenon is a direct and observable signature of the universe's ongoing growth, a tranquil and pervasive indicator of its dynamic nature, gently altering the luminous messages from the cosmic past. This cosmological redshift is an indispensable tool for astronomers, allowing them to measure the distances to very distant galaxies and, in turn, understand the universe's expansion history. By analyzing the precise amount of redshift in the light received from a galaxy, scientists can calculate. This, in turn, provides a highly accurate measure of the galaxy's distance from us. The greater the redshift, the farther away the galaxy, and the further back in cosmic time we are looking. This method allows astronomers to construct a three-dimensional map of the universe, tracing the distribution of galaxies across billions of light years. More profoundly, By studying the redshift of countless galaxies across different epochs, scientists can piece together the entire history of cosmic expansion, revealing how the universe's growth rate has changed over billions of years, from its early rapid inflation to its current accelerating expansion driven by dark energy. It is a serene and powerful form of cosmic archaeology, using the subtle stretching of light to reconstruct the grand narrative of the universe's unfolding, its dynamic past and present. This quiet analysis of light's altered journey allows us to decipher the universe's autobiography, written in the very fabric of space-time, arrive at a profound insight into the very nature of reality itself, a revelation brought forth by the unwavering speed of light. The speed of light fundamentally connects space and time, weaving them together into the unified, four-dimensional concept known as space-time. Before Einstein, space was largely considered a static stage, and time a universal, unyielding river flowing independently. However, the consistent velocity of light, regardless of an observer's motion, demonstrated that these two dimensions are not separate entities, but intrinsically interwoven components of a single, dynamic fabric. Imagine a vast, shimmering tapestry, where every thread of space is intricately laced with threads of time, forming an inseparable whole. The speed of light acts as the fundamental constant that dictates the geometry and flexibility of this cosmic tapestry. It dictates how motion through one dimension, such as space, inevitably influences our experience and measurement of the other, time. This elegant unification means that our universe is not merely three spatial dimensions plus a separate temporal one, but a continuous, four-dimensional continuum where all events unfold. This concept invites a serene contemplation of the universe as a singular, flowing entity, where the boundaries between space and time blur into a harmonious, interconnected existence, a silent testament to the deep, underlying unity of cosmic principles. It reveals a universe far more integrated and beautifully symmetrical than our everyday perceptions might suggest, ensuring a consistent and profound reality across all perspectives and velocities. Within this unified fabric of space-time, every event, whether it is a star igniting, a planet orbiting, or even a single thought forming, possesses a unique and intrinsic structure known as a light cone. This ethereal geometric construct defines the possible future and past paths of light and matter relative to that specific event. Imagine an event as the apex of two cones, one extending into the future and the other into the past, meeting at that single point in space-time. The future light cone encompasses all locations and moments that can be causally influenced by the event, representing the furthest reach of its effects. Conversely, the past light cone comprises all locations and moments from which a signal, traveling at or below the speed of light, could have reached the event, thus defining its potential causes. Anything outside these light cones is causally disconnected from the event, meaning it could neither influence it nor be influenced by it. This elegant concept profoundly organizes the universe's causal structure, ensuring that information and influence propagate in an orderly, unhurried manner, always adhering to the cosmic speed limit. It is a tranquil map of possibility and history, gently guiding our understanding of cause and effect across the vastness of space-time, revealing the profound interconnectedness and limitations of cosmic influence. For light itself, its path is always precisely along the very boundary or surface of this light cone, traveling at the maximum possible speed. Photons, being massless particles, are inherently compelled to move, see. This means that their trajectory through spacetime is perfectly aligned with the edges of these light cones. Any particle with mass, such as an electron or a planet, must always travel within the light cone, never reaching its boundary, because anything with mass is forever bound to speeds less than c. The light cone therefore acts as a universal speed governor, delineating the absolute fastest possible path through spacetime for any form of energy or information. For light, this boundary is its natural, unyielding highway, a path it traverses with serene and unwavering consistency. This fundamental characteristic underscores the unique nature of light as the universe's ultimate messenger, always moving at the fastest possible pace, defining the very limits of causal connection across the cosmos. It is a quiet, yet powerful, illustration of how the speed of light shapes the fundamental geometry of space-time, ensuring that the universe unfolds with a predictable and elegant order, a continuous and silent journey along the edges of time and space. For all observers, leads to one of the most counterintuitive, yet deeply verified implications of special relativity, the relativity of simultaneity. This means that different observers, moving at different velocities relative to one another, may genuinely disagree on whether two events happened at the same time. Our everyday experience, where we assume that now is the same moment for everyone, is merely an approximation that holds true at low speeds. However, at relativistic velocities, this intuitive notion gently dissolves. There is no absolute universal now that all observers can agree upon. Instead, simultaneity becomes relative to an observer's frame of reference. This is not an illusion or a perceptual trick, but a fundamental property of space-time itself, a direct consequence of light's constant speed. It is a profound and elegant concept that challenges our most basic assumptions about time, revealing a universe where the flow of moments is not a synchronized, universal rhythm, but a more nuanced and observer-dependent experience. This subtle, yet significant shift in perspective, maintaining a serene harmony within the cosmic design, even as individual experiences of time diverge. To further illustrate this captivating concept, imagine two distant events, perhaps two gentle flashes of light occurring in different locations. For one observer, standing stationary between these two flashes, the light from both events might reach them at precisely the same moment, leading them to conclude that the events happened simultaneously. However, for another observer, moving swiftly past the first observer in a high-speed spacecraft, those same two flashes would not appear to occur at the same time. Due to their motion, one flash's light would appear to reach them before the other, and they would genuinely perceive the events as happening sequentially, not simultaneously. Both observers' perceptions are equally valid according to the laws of physics, despite their disagreement on the simultaneity of the events. This profound difference arises because the speed of light remains constant for both observers, and the geometry of space-time subtly adjusts to accommodate this unwavering truth. It is a serene and elegant demonstration of how motion influences our perception of time and space, revealing that now is a deeply personal and relative experience in the vastness of the cosmos, a quiet whisper of the universe's flexible temporal tapestry, gently unfolding differently for each unique journey through its expanse. Shifting our focus to another subtle aspect of light's interaction with the physical world, we encounter the phenomenon of light pressure, also known as radiation pressure. This is the gentle physical pressure exerted by electromagnetic radiation on any surface it strikes, while photons, the particles of light. When these tiny packets of energy gracefully collide with a surface, they transfer a minuscule amount of this momentum, imparting a subtle force. Imagine a continuous, gentle stream of countless microscopic particles softly nudging a surface. That is the essence of light pressure. This pressure is incredibly subtle, far too imperceptible for us to feel in our daily lives. The light from a flashlight, or even the intense beam of a laser, will exert an immeasurably small force on your hand. However, over vast periods and with immense sources of light, this delicate pressure can accumulate to have significant effects, shaping cosmic environments and influencing the movement of celestial dust. It is a tranquil testament to the dual nature of light, behaving as both a wave and a particle, and demonstrating that even the most ethereal forms of energy possess a tangible, albeit gentle, physical presence, capable of exerting a quiet, persistent influence across the cosmos. This subtle yet persistent light pressure, though incredibly gentle, is the fascinating principle behind visionary concepts like solar sails. These futuristic spacecraft aim to harness only the momentum of sunlight to propel themselves through the vacuum of space, entirely without the need for conventional rocket fuel. Imagine vast, incredibly thin, and highly reflective membranes, perhaps several acres in size, unfurling gracefully in the emptiness of space. As countless photons from the sun gently strike these immense sails, they impart their tiny momentum, creating a continuous, subtle push. This force, while weak, is constant and cumulative. Over long periods, this unhurried, patient propulsion can accelerate a spacecraft to very high velocities, allowing for efficient, long-duration interstellar or interplanetary travel. Unlike traditional rockets that burn through finite fuel, a solar sail would have an effectively limitless source of propulsion as long as it is bathed in starlight. It is a beautiful, serene example of how humanity seeks to align its technological aspirations with the fundamental laws of the cosmos, utilizing the quiet, pervasive energy of light to embark on voyages of exploration. This concept transforms the subtle nudge of photons into a powerful, sustainable means of cosmic travel, a tranquil and elegant vision for the future of humanity's gentle wanderings among the stars, silently propelled by the very essence of cosmic illumination. As we conclude our journey through the wondrous properties of light, let us reflect on its deepest implications, those that touch upon the very structure of reality and the ultimate destiny of the cosmos. This foundational pillar of physics ensures a principle that is absolutely vital for the coherent functioning of our universe, the principle of causality. This profound law dictates that cause always precedes effect, maintaining a predictable and orderly sequence of events throughout the entirety of space-time. The fact that no information can travel faster than light means that it is impossible to send a signal or influence any event backward in time. If information could exceed c, one could theoretically send a message to the past, altering a past event and thereby creating a paradox where a cause could be negated by its own future effect. The cosmic speed limit, therefore, acts as a serene guardian of the universe's timeline, preventing such temporal anomalies and ensuring that the flow of history is always forward, always consistent. It is a fundamental truth that underpins our understanding of existence, establishing an unyielding boundary that preserves the logical progression of cause and consequence across the vast, tranquil expanse of the cosmos. This immutable law is not a dramatic restriction, but a graceful constraint, allowing for the steady evolution of stars, galaxies, and life itself within a consistent temporal framework. Without this inherent speed limit, the very fabric of reality, with its clear distinction between past, present, and future, would simply unravel into an incomprehensible chaos. It is the silent, unwavering sentinel that guards the integrity of time, ensuring that the universe remains a place of discernible order and serene progression, where every moment gracefully leads to the next without disruption or paradox. This profound guarantee of causality is perhaps the most significant implication of light's constant speed, offering a tranquil assurance of cosmic stability. Finally, our comprehensive understanding of the speed of light proves to be an indispensable key to predicting the ultimate fate of the universe itself. This cosmic constant is intricately woven into the dynamics of cosmic expansion, influencing how galaxies drift apart and how the universe evolves over billions of years. Measurements of light from distant galaxies, stretched by cosmological redshift, allow astronomers to trace the history of this expansion, revealing its current rate and acceleration. This rate, in turn, is profoundly influenced by the enigmatic behavior of dark energy, the mysterious force that is pushing the universe's expansion to speed up. The speed of light is the fundamental factor that calibrates our observations of this dark energy, allowing us to quantify its effects and understand its potential long-term influence on the cosmos. Will the universe continue to expand forever, eventually becoming a cold, empty expanse in a big freeze? Or will the accelerating expansion tear apart even galaxies and atoms in a big rip? The answers to these profound questions are intimately tied to the precise interplay between the speed of light, the density of matter, and the nature of dark energy. Furthermore, C governs the fundamental interactions that shape our cosmos. From the delicate dance of subatomic particles to the grand processes of stellar evolution and galactic formation, it is the unifying constant in Einstein's mass-energy equivalence, E equals mc squared, which explains how stars generate their radiant energy and how the elements essential for life are forged. Without a thorough grasp of light's speed, our models of the universe's past, present, and future would be incomplete, lacking the foundational precision needed to truly comprehend its majestic unfolding. The speed of light is therefore not just a measure of velocity, but a profound parameter that anchors our entire cosmological framework, guiding our predictions about the universe's long-term destiny. It is the silent, elegant thread that weaves together all the grand cosmic forces and phenomena, allowing us to glimpse the serene, majestic path that the universe is patiently taking, from its fiery birth to its distant, ultimate fate. This deep connection invites us to contemplate the profound cosmic ballet, where every interaction, every expansion, and every future possibility is subtly orchestrated by the unwavering pace of light, a continuous, harmonious symphony of universal laws. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of light's unwavering speed to its profound influence on the very fabric of space-time. From the intricate dance of photons with matter to the gentle cosmic expansion, you have traveled through ethereal realms, soared alongside invisible waves, and glimpsed the heart of the universe glowing softly across unimaginable distances.